This galaxy is watching us. From 23 million light-years away, the Whirlpool Galaxy hangs in the constellation Canes Venatici like a blueprint the universe left out in the open. Perfectly formed spiral arms, brilliant blue star clusters tracing graceful curves across 76,000 light-years of space. Astronomers call it the Grand Design, and for more than 2 centuries, it has been one of the most photographed, most studied, most iconic objects in the night sky. We have mapped its structure, we have measured its light, we have built entire theories of galactic evolution around what we see when we point our telescopes at M51. And yet, the deeper we look, the stranger it becomes. Because those spiral arms are not spinning the way you think they are. The stars inside them are not moving together. The arms themselves are not solid. They are waves, density waves, cosmic traffic jams where gas piles up, compresses, ignites and dies in a cycle that has been running for hundreds of millions of years. And at the center of it all, buried beneath layers of dust and starlight, there is something pulling. A supermassive black hole, millions of times the mass of our sun, feeding, warping space-time itself, holding the entire galaxy in its grip. This is not a documentary about a pretty picture in space. This is about what happens when you travel 23 million light-years to see what is actually there. When you go past the image, past the light, all the way down to the fires of creation and the mouth that swallows everything. Because what we found at the heart of the Whirlpool Galaxy changes how we understand our own. This is that journey. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. There is a galaxy 23 million light-years from the chair you are sitting in that looks exactly the way a galaxy is supposed to look. Not in the messy, chaotic, lopsided way most galaxies actually turn out when you point a telescope at them. Not in the elliptical blob way or the irregular smudge way or the barely there dwarf way. This one looks like the platonic ideal of a spiral galaxy, the kind a child would draw if you handed them a crayon and said, "Make me a galaxy." 2 perfect arms, sweeping outward from a bright core in a symmetrical curl that looks less like an accident of gravity and more like a blueprint. Astronomers have a name for galaxies like this. They call them Grand Design spirals. And the most famous example in the entire night sky, the one that shows up in textbooks and posters and desktop wallpapers across the planet, is Messier 51, the Whirlpool Galaxy. The name fits. If you have ever watched water spiral down a drain or cream swirl into coffee or a hurricane rotate on a satellite feed, you have seen the shape. The galaxy looks like motion frozen in time, like someone hit pause on a cosmic vortex mid-spin. 2 luminous arms wrap around the core in a near-perfect logarithmic spiral, studded with bright knots of blue and pink where stars are being born by the thousands. At the end of one of those arms, connected by a faint bridge of light, sits a smaller companion galaxy, NGC 5195, caught in the act of grazing past. The whole system looks like a painting. It does not look like something that assembled itself through 14 billion years of chaos. And that is the first thing you need to understand about M51. It is not supposed to look this good. Galaxies are messy. They collide, they warp, they get stretched by dark matter halos and shredded by tidal forces and pummeled by smaller galaxies that wander too close. Most spiral galaxies have asymmetric arms, or multiple fragmented arms, or arms that fade out halfway around, or no clear arms at all. The Grand Design spirals, The ones with two dominant symmetric arms like M51 make up less than 10% of all spiral galaxies in the observable universe. They are the exception, they are the showcase, and for more than 2 centuries, astronomers have been trying to figure out how they got that way. The Whirlpool was discovered on October 13, 1773, by Charles Messier, a French astronomer who spent his career hunting comets. Messier was good at his job. He found 13 comets over his lifetime, which in the 18th century was enough to make you famous. But his legacy is not the comets. His legacy is the list he made of things that were not comets. Fuzzy patches in the sky that looked like comets through a small telescope but did not move. Messier catalogued them so other comet hunters would not waste their time. He had no idea what most of them were. He just knew they were annoying. Object number 51 on his list, spotted in the constellation Canes Venatici just below the handle of the Big Dipper, was one of those annoyances. A faint smudge of light, unremarkable except for the fact that it refused to go anywhere. Messier noted it, sketched it, moved on. His drawing shows a single fuzzy blob with a smaller blob nearby. No spiral arms, no detail, just fog. That was not his fault. The telescopes of the era were not powerful enough to resolve structure in objects that far away. It would be another 70 years before anyone saw the Whirlpool the way we see it now. That honor went to William Parsons, the 3rd Earl of Ross, an Irish aristocrat with enough money to build the largest telescope on Earth and enough curiosity to point it at Messier's catalogue. In 1845, Parsons aimed his 72-inch reflecting telescope, a beast of a machine he called the Leviathan, at M51. What he saw through the eyepiece that night changed astronomy. Spiral structure. Clear, unmistakable, winding arms extending from a bright nucleus. He sketched what he saw, published the drawing, and the astronomical community lost its collective mind. Nobody knew what spirals meant. The prevailing theory at the time was that all nebulae, which is what they called these fuzzy objects, were clouds of gas inside the Milky Way, possibly solar systems in the process of forming. Parsons' discovery complicated that story. If nebulae were local gas clouds, why did some of them have spiral shapes? Why did they look so organized? The debate raged for decades. Some astronomers argued that spiral nebulae were rotating disks of material collapsing into new stars. Others suggested they were entire separate star systems far beyond the Milky Way, what we would today call galaxies. The argument was not settled until the 1920s when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson to measure the distance to the Andromeda Nebula. He found Cepheid variable stars inside it, pulsating stars whose brightness could be used to calculate distance. The numbers came back unambiguous. Andromeda was not a cloud inside the Milky Way. It was nearly 1 million light-years away, a separate galaxy entirely. Once Hubble proved that Andromeda was external, the rest of the spiral nebulae fell into place. M51 was not a gas cloud. It was a galaxy, a massive rotating island of hundreds of billions of stars sitting 23 million light-years across the void. And those spiral arms Parsons had sketched were not an optical illusion or an artifact of his telescope. They were real structures, vast sweeping layings of stars and gas stretching across tens of thousands of light-years. The Whirlpool became famous almost immediately. It was close enough and bright enough and face-on enough that every major telescope in the world could study it in detail. By the mid-20th century, M51 was one of the most photographed objects in the sky. The face-on orientation is what makes it so useful. Most spiral galaxies we observe are tilted at an angle, which makes it hard to see the arm structure clearly. Some are edge-on, which gives you a beautiful thin disk view but hides all the internal detail. M51 sits almost perfectly perpendicular to our line of sight, like someone laid it flat on a table and told us to take notes. That geometry turns the galaxy into a textbook. You can trace the arms from the core all the way out to the edges. You can map where the stars are forming. You can measure the density of gas in different regions. You can watch how the companion galaxy, NGC 5195, distorts the outer arm as it swings past. Every feature is visible. Every process is on display. The whirlpool is not just beautiful, it is legible. The spiral arms themselves are the main event. In the most famous images of M51, taken by the Hubble Space Telescope and later by the James Webb Space Telescope, the arms glow with a mix of colors that tell the story of what is happening inside them. The core of the galaxy is yellow-orange, the color of older stars, red giants and sun-like stars that have been burning for billions of years. The arms are blue and pink. Blue from young massive stars, hot and bright and burning through their fuel at a ferocious rate. Pink from ionized hydrogen gas, lit up by the ultraviolet radiation pouring out of those same young stars. The pink regions are called H2 regions, and they mark the locations of active star formation. Everywhere you see pink in M51, stars are being born right now. The European Space Agency's Hubble team described the arms as a grand spiral staircase sweeping through space. NASA called them star formation factories. Both descriptions are accurate. The arms are not solid structures. They are not like the arms of a pinwheel that you could grab and spin. They are density waves, regions where gas and dust pile up as the galaxy rotates. Think of traffic on a highway. Cars move at different speeds, but every so often they bunch up into a slow-moving clump. That clump is not made of the same cars for very long. Cars enter the clump from behind, slow down, then speed up and leave from the front. But the clump itself, the region of higher density, persists. It moves along the highway at its own speed, independent of the individual cars. The spiral arms of M51 work the same way. Gas clouds orbit the galaxy at different speeds depending on how far they are from the center, but the arms themselves, the regions of higher density, rotate at a fixed pattern speed. As gas clouds enter an arm, they slow down, compress, and collapse under their own gravity. Stars ignite, the clouds light up. Then the newborn stars drift out of the arm and continue their orbits while new gas drifts in behind them. This is why the arms are blue. Massive stars, the kind that shine blue, only live for a few million years. By the time they drift out of the spiral arm where they were born, they are already dying. The arm stays bright because new stars keep forming inside it. A conveyor belt of birth and death that has been running for billions of years. The whole process is efficient, relentless, and visible. M51 is showing us in real time how spiral galaxies build themselves. The galaxy is big. Estimates put its diameter at around 60,000 light-years, roughly half the size of the Milky Way. It contains something in the neighborhood of 160 billion solar masses worth of material, stars and gas and dust and dark matter, all held together by gravity. That mass is not distributed evenly. Most of the stars live in the central bulge and the disk. The spiral arms are not where most of the stars are. They are where most of the action is. The arms are the frontier, the place where the galaxy is actively growing, turning raw hydrogen into new suns. At the very center of M51, buried beneath the yellow glow of the core, there is a supermassive black hole. We cannot see it directly. Black holes do not emit light, but we can see the effects. The core of the galaxy is unusually bright in certain wavelengths, particularly in X-rays. That brightness is a signature of matter falling into the black hole, heating up to millions of degrees as it spirals inward, radiating energy before it crosses the event horizon and disappears. Astronomers classify M51 as a Seyfert galaxy, a type of active galaxy where the central black hole is feeding but not aggressively enough to qualify as a full quasar. It is a low-level furnace ticking away at the heart of the system. The Chandra X Ray Observatory has spent years mapping M51 in high-energy light. It has identified nearly 500 X-ray sources scattered across the galaxy and its companion. Most of those sources are neutron stars and stellar mass black holes, the remnants of massive stars that exploded as supernovae and left behind dense cores. A handful of the sources are ultra-luminous, shining brighter than any single star should be able to shine. Those are likely intermediate mass black holes or neutron stars pulling matter off companion stars at extreme rates. Every one of those sources is a story. Every one is a star that died violently, leaving behind something strange. The distance to M51 is usually given as 23 million light-years. Some references say 25 million. Some say 31 million. The spread comes from the difficulty of measuring distances to objects that far away. Astronomers use a technique called the cosmic distance ladder, starting with nearby objects whose distances can be measured directly and bootstrapping outwards step by step to more distant galaxies. Each step introduces uncertainty. By the time you reach M51, the error bars are a few million light-years wide. For most purposes, that does not matter. Whether the galaxy is 23 or 31 million light-years away does not change what we see or how we interpret it. It just means the light we are looking at left the galaxy 23 or 31 million years ago, long before humans existed, long before our ancestors climbed down from the trees. What makes M51 special is not that it is close, though being relatively nearby certainly helps. It is not that it is big, though size matters when you are trying to study internal structure. What makes M51 special is that it is perfect, or at least as close to perfect as a galaxy gets. The symmetry, the clarity, the face-on view, the active star formation, the interacting companion, the supermassive black hole, the X-ray sources, the sheer visual spectacle of the thing, every feature you would want in a laboratory for studying how galaxies work is present in M51. It is the reference galaxy, the one astronomers point to when they want to explain what a grand design spiral looks like and why spiral arms exist, and how star formation proceeds in a rotating disk. If you wanted to design a galaxy specifically to teach students and researchers how galaxies behave, you would build M51. And yet, for all that perfection, the galaxy is still full of questions. Why does it have only 2 arms when some spirals have 4 or 6 or none? How long have those arms been stable? What role does the companion galaxy play in maintaining the structure? How fast is the black hole at the center growing? How many stars have been born in the arms over the last billion years? How many have died? The Whirlpool is one of the most studied galaxies in the sky, observed in every wavelength from radio to gamma rays, and we are still finding new details every time we look. The journey ahead is going to take us deep into that structure. We are going to pull apart the spiral arms and see how they really work. We are going to watch stars being born and watch them die. We are going to look at the black hole and ask what it is doing to the galaxy around it. We are going to trace the collision between M51 and its companion and figure out how much of the Whirlpool's beauty is owed to that cosmic fender bender. And we are going to step back at the end and ask what M51 tells us about galaxies in general, about the Milky Way, about the structures that fill the universe. But first, we need to understand how the spiral got there in the first place. Because those arms, the grand sweeping staircase, the star formation factories, the defining feature of the entire system, did not just appear, they were built. Or more accurately, they were pulled into existence by forces that have been acting on this galaxy for millions of years, forces that are still acting right now. The Whirlpool did not become the Whirlpool by accident. It had help, and that help came from the small, irregular galaxy sitting at the end of one of its arms, locked in a slow gravitational waltz that has been reshaping both galaxies for tens of millions of years. That is where the story really begins. The thing at the end of the arm is not supposed to be there, or more accurately, it is not supposed to look the way it does. In every glossy image of the Whirlpool Galaxy, in every textbook photo and planetarium slide and desktop background, there is a yellowish blob smeared across the tip of one of M51's spiral arms, like a paint smudge that somebody forgot to clean up. That blob has a name, NGC 5195, and it is not a smudge, it is a galaxy. A smaller, older, messier galaxy that wandered too close to the Whirlpool millions of years ago and never left. The two have been locked in a gravitational embrace ever since, circling each other, pulling on each other, reshaping each other in ways that are still playing out right now. And the reason M51 looks the way it does, the reason it has those perfect sweeping arms, the reason it became the poster child for grand design spirals in the first place, is because of that collision. The Whirlpool did not build itself. It had help, violent help. NGC 5195 is small. Estimates put its mass at roughly 1/10 that of M51, maybe less. It is an irregular dwarf galaxy, the kind of object that in isolation would barely register as interesting. No grand spiral arms, no organized structure, just a clump of old stars drifting through space. If you pointed a telescope at NGC 5195 by itself, you would see a faint fuzzy patch and move on. But it is not by itself. It is caught in the act of grazing past one of the largest, most organized spiral galaxies in the local universe, and that proximity has turned both galaxies into something neither would have been on its own. The interaction was first noticed in the mid-20th century when astronomers started taking long-exposure photographs of M51 with large telescopes. Early images showed a faint bridge of material connecting the two galaxies, a thin streamer of gas and stars stretching from the outer arm of M51 directly into NGC 5195. That bridge was the smoking gun. Galaxies do not grow bridges by accident. They grow them when gravity pulls material from one object to another. The two galaxies were not just sitting near each other in space. They were tearing pieces off each other. By the 1970s, astronomers had developed computer simulations sophisticated enough to model what happens when two galaxies pass close to one another. The math is brutal. Every star in each galaxy is pulling on every other star through gravity. Every cloud of gas, every speck of dust, every atom of hydrogen is responding to the combined gravitational field of both galaxies at once. You cannot solve that problem by hand. You need a computer to track the motion of millions of individual particles over millions of years of simulated time. The early simulations were crude, but they worked. Feed in the masses and velocities and distances, let the simulation run, and out comes a prediction for what the galaxies should look like at different points in their interaction. When researchers ran those simulations on M51 and NGC 5195, the results matched the observations almost perfectly. The bridge, the distorted arm, the lopsided structure of the companion galaxy, all of it fell out of the equations naturally. The model showed that the two galaxies had already passed by each other at least once, maybe twice, and were still in the middle of a slow-motion collision that had been unfolding for tens of millions of years. Here is how the dance works. NGC 5195 is not orbiting M51 the way a moon orbits a planet. It is not trapped in a stable circular path. It is on a trajectory more like a comet, a long elliptical loop that carries it far away from the whirlpool for millions of years at a time before swinging back in for another close pass. The last close approach happened somewhere between 50 and 100 million years ago. The exact timing is hard to pin down because the data has error bars and the simulations have free parameters you can adjust. But the broad story is clear. NGC 5195 came screaming in from the outer halo, passed within a few tens of thousands of light-years of M51's disk, and got caught by the larger galaxy's gravity. It did not crash head-on, it sideswiped. The encounter was violent enough to distort both galaxies, but not violent enough to destroy either one outright. Instead, the two galaxies exchanged momentum and material, then continued on their separate paths, now bound together in a slow decaying orbit that will eventually end with a full merger. The effects of that first pass are written all over M51. Before the collision, the galaxy probably had spiral arms, but they would have been weaker, less defined, more like the messy multi-arm spirals you see in most disk galaxies. The gravitational tug from NGC 5195 acted like a wrench thrown into a spinning wheel. It did not stop the wheel, it organized it. As the companion galaxy passed by, its gravity pulled on the outer regions of M51's disk, creating a ripple that propagated inward through the gas and stars. That ripple became a density wave, a regions where material piled up as it moved through the disk. And because the ripple had a specific shape and a specific rotation rate, it forced the gas clouds in the disk to follow that pattern. The result was two dominant spiral arms instead of 4 or 6 fragmented ones. The collision took a messy system and gave it structure. Tidal forces are what make this possible. When an object is large enough and close enough to another object, the gravity acting on the near side is stronger than the gravity acting on the far side. That difference in pull stretches the object along the line connecting the two bodies. You see this on Earth every day. The moon's gravity pulls on the oceans, creating a bulge on the side of the Earth facing the moon, and another bulge on the opposite side. Those bulges are the tides. The same physics applies to galaxies, but the stakes are higher. When NGC 5195 passed by M51, the tidal forces stretched the outer disk, pulling gas and stars outward in the direction of the companion. Some of that material escaped entirely, forming the bridge that connects the two galaxies. Some of it stayed behind, but in a distorted configuration that took millions of years to settle. The spiral arms we see today are the aftershock of that encounter, a pattern frozen into the structure of the galaxy by the gravitational chaos that followed. The bridge itself is one of the most striking pieces of evidence for the interaction. It is faint, easy to miss in casual images, but deep exposures reveal a thin streamer of stars and gas extending from M51 directly into the body of NGC 5195. That streamer is made of material that used to belong to the whirlpool. During the close pass, the tidal forces were strong enough to rip gas clouds and even whole star clusters out of the outer disk and fling them toward the companion galaxy. Some of that material fell into NGC 5195. Some of it is still drifting in the space between the two galaxies, slowly dispersing into the intergalactic medium. The bridge is temporary. In a few tens of millions of years, it will fade as the material spreads out and dims. But for now, it is a visible scar, a record of the violence that reshaped both galaxies. NGC 5195 did not escape unscathed. The smaller galaxy is visibly distorted, stretched and warped by the same tidal forces that organized M51's spiral arms. Its stars are no longer distributed symmetrically. One side of the galaxy is brighter and more compact than the other, the side that faced M51 during the last encounter. The gas content of the companion has been partially stripped away, either pulled into M51 or dispersed into the halo. What remains is an older stellar population, yellowish stars that have been burning for billions of years, with very little ongoing star formation. The galaxy looks tired. It looks like something that has been through a collision and is still recovering. The interaction also triggered a burst of star formation in M51. When tidal forces compress gas clouds, they push the gas past the threshold where it can collapse under its own gravity and ignite into new stars. The spiral arms of the whirlpool are packed with young blue stars and pink H2 regions, the signature of active starbirth. Some of that activity would have happened anyway. Spiral arms naturally compress gas as it moves through them. But the collision with NGC 5195 amplified the process, dumping extra gas into the disk and creating larger, denser clouds than would have formed otherwise. The result is a galaxy that is forming stars faster than it would be if it were left alone. Astronomers call this a starburst, a temporary spike in star formation driven by an external trigger. M51 is not a full starburst galaxy, the kind where the entire disk lights up like a firework. But it is elevated. The collision left a mark, and that mark is still glowing. One of the most useful tools for understanding the interaction has been computer simulations. Modern models can track the motion of millions of particles over hundreds of millions of years of simulated time, adjusting the parameters until the output matches the real observations. Researchers start with estimates for the masses of the two galaxies, their velocities, the angle of the encounter, and the distance of closest approach. Then they run the simulation forward and see what happens. If the model predicts a bridge where no bridge exists, they adjust the parameters and try again. If it predicts spiral arms that are too tight or too loose, they tweak the masses or the speeds and rerun the calculation. Over time, through trial and error, the model converges on a set of parameters that reproduces the observed structure of M51 and NGC 5195. Those parameters tell you what actually happened. How fast the galaxies were moving, how close they came, how much material was exchanged. The simulations have revealed several surprising details. One is that the encounter was not head-on. NGC 5195 approached M51 at an angle, grazing the outer disk rather than plowing straight through the center. That grazing geometry is what allowed the spiral arms to survive. A direct collision would have shredded the disk entirely, turning M51 into a chaotic mess of stars and gas with no organized structure. The glancing blow was just violent enough to reshape the galaxy without destroying it. Another surprise is that the two galaxies are still interacting. The first pass happened tens of millions of years ago, but the gravitational influence of NGC 5195 is still affecting M51's structure. The outer arm is still distorted, still being pulled toward the companion. The system has not reached equilibrium. It is in the middle of a process that will take another few 100 million years to complete. The eventual fate of the system is a merger. NGC 5195 is losing energy every time it swings past M51, shedding orbital momentum through tidal interactions. Each pass brings the two galaxies a little closer together. Eventually, after a few more close encounters, the companion will fall into the whirlpool, and the two will combine into a single larger galaxy. What that final product will look like depends on the details of the merger. If the collision happens slowly, with NGC 5195 spiraling inward over hundreds of millions of years, the Whirlpool's disk might survive more or less intact, swallowing the smaller galaxy without losing its spiral structure. If the collision happens quickly, with a sudden plunge into the core, the disk could be disrupted entirely, transforming M51 into an elliptical galaxy or an irregular blob. The simulations suggest the former is more likely, but the uncertainties are large. Predicting the future of a galaxy collision is hard. Too many variables, too much chaos. The interaction between M51 and NGC 5195 is not unique. Galaxy collisions are common in the universe. The Milky Way is currently in the process of devouring several smaller dwarf galaxies, shredding them into streams of stars that wrap around our galaxy like ribbons. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy in a slow-motion crash that will take hundreds of millions of years to complete. The products of past collisions are everywhere. Elliptical galaxies, the giant featureless blobs that dominate the centers of galaxy clusters, are thought to be the remnants of major mergers between spiral galaxies. Irregular galaxies, the shapeless clumps of stars that do not fit into any clean category, are often the result of gravitational interactions that tore apart whatever structure they once had. Collisions are how galaxies grow. They are how large galaxies get larger, how gas gets funneled into the centers of galaxies to feed supermassive black holes, how bursts of star formation are triggered. The universe is full of galaxies eating each other. What makes M51 special is that we are catching it in the act, at a moment when the interaction is still visible but not yet complete. The collision happened recently enough that the evidence is still fresh. The bridge has not faded. The spiral arms are still well defined. The companion galaxy is still intact, not yet fully absorbed, and the whole system is close enough and bright enough that we can study it in exquisite detail. M51 is a laboratory. It is showing us in real time what happens when two galaxies collide, how tidal forces reshape disks, how star formation responds to compression, how spiral structure emerges from chaos. Every observation we make of the Whirlpool teaches us something about how galaxies in general evolve over cosmic time. The simulations have also clarified the role of dark matter in the interaction. Both M51 and NGC 5195 are embedded in halos of dark matter, invisible material that dominates the mass of each galaxy but does not emit light. The dark matter halos extend far beyond the visible disks, creating a gravitational field that affects the motion of both galaxies long before their stars come close to touching. When the two halos collided, they transferred momentum and energy, slowing down the companion galaxy and altering its trajectory. The visible interaction, the bridge and the distorted arms, is just the tip of the iceberg. Most of the gravitational chaos is happening in the dark matter, where we cannot see it directly. We infer it from the motion of the stars and gas, from the way the galaxies are moving and the speeds at which they are orbiting each other. The dark matter is the scaffolding. The stars and gas are just the decoration. One of the open questions is how many times NGC 5195 has passed by M51. Some models suggest this is the second or third encounter. Others argue it is the first. The evidence is ambiguous. If there were previous passes, they should have left traces in the structure of the galaxy, subtle asymmetries or extra distortions that the current models could detect. But the data is noisy and the simulations have free parameters. Different research teams have arrived at different conclusions, and the debate continues. What everyone agrees on is that the interaction is ongoing, and that the two galaxies will merge eventually. The question is not if, but when, and what the intermediate stages will look like. The interaction has also affected the central regions of M51. The supermassive black hole at the core of the galaxy is more active than it would be in an isolated spiral. The collision funneled gas inward toward the center, feeding the black hole and triggering bursts of emission in X-rays and other high-energy wavelengths. The Chandra X Ray Observatory has detected strong emission from the core, consistent with a black hole accreting matter at a moderate rate. The galaxy is not a full quasar, where the black hole outshines the entire galaxy, but it is not dormant either. It is ticking over, pulling in gas and radiating energy, a direct consequence of the gravitational chaos stirred up by the collision with NGC 5195. Without that collision, the black hole would likely be quieter, starved of fuel, sitting idle at the center of a stable disk. The bridge between the two galaxies is not just gas. It contains stars, whole stars that were ripped out of one galaxy and flung toward the other. Those stars are now orphaned, no longer part of either galaxy in any meaningful sense. They are drifting through intergalactic space, bound loosely to the system, but not embedded in a disk or a halo. Over time, some of them will fall back into one of the galaxies. Others will escape entirely, ejected into the void by the chaotic gravitational field of the collision. These orphan stars are a new population, created by the interaction, and they will persist long after the bridge itself has faded. Decades from now, when the two galaxies have merged into a single object, there will still be stars in the halo that remember the collision, stars whose orbits are strange and eccentric because they were born in one galaxy and stolen by another. The interaction also provides a natural laboratory for testing theories of spiral structure. Before M51, astronomers had two competing ideas for how spiral arms form. One theory said the arms were material structures, like the spokes of a wheel, rotating rigidly with the disk. The other said they were density waves, patterns that move through the disk independently of the stars and gas. The collision with NGC 5195 settled the debate in favor of density waves. The tidal forces from the companion triggered a wave that propagated through the disk, creating the two dominant arms we see today. Those arms are not made of the same material over time. Stars and gas drift in and out of the arms as they orbit the galaxy, but the pattern itself persists, rotating at a fixed speed, independent of the individual particles. M51 proved that spiral arms are waves, not structures, and that insight changed the way astronomers think about every spiral galaxy in the universe. The story of M51 and NGC 5195 is still being written. The galaxies are still interacting, still pulling on each other, still reshaping each other with every passing million years. The next close encounter is millions of years away, but it is coming. The orbits are decaying, the distance is shrinking. Eventually, the two will merge, and the whirlpool as we know it will cease to exist. What replaces it will be something new, something larger, something shaped by the collision in ways we can only guess at. For now, we have this moment. The moment when the spiral arms are perfect, when the companion is still visible at the end of the arm, when the bridge is still faint but detectable, when the whole system is frozen in a configuration that will never repeat. We are lucky to see it. We are lucky to have the telescopes and the simulations and the data to understand it. And we are lucky that the universe, in its vast chaotic indifference, placed this collision close enough and oriented just right for us to study. The spiral arms themselves are the legacy of the collision. They are the fingerprint of the gravitational chaos that reshaped the galaxy millions of years ago. But the arms are not static. They are moving, rotating, evolving. Gas is flowing through them. Stars are being born inside them. The whole structure is alive, responding to forces that are still playing out across tens of thousands of light years. And that motion, that flow, is what we turn to next. The arms do not rotate. That is the first thing you need to get out of your head if you want to understand how M51 actually works. Look at any photograph of the Whirlpool Galaxy and your brain will tell you a story. It will tell you that those bright, sweeping arms are solid structures, like the blades of a pinwheel or the spokes of a wheel, spinning around the center in a stately rotation that has been going on for billions of years. Your brain will tell you that the stars in the arms are moving together, that the whole pattern is rotating as a single rigid object, that if you could watch the galaxy for a few million years, you would see the arms sweep around the core like clock hands. Your brain is lying to you. The arms are not rotating the way they appear to be. The stars inside the arms are not moving together. And the pattern you are seeing, the grand sweeping spiral that makes M51 famous, is not a structure at all. It is a wave. This is not a small distinction. It is the difference between understanding how spiral galaxies work and fundamentally misunderstanding them. For decades, astronomers believed the arms were material features, real physical structures embedded in the disk that rotated with the stars. The idea made intuitive sense. Galaxies rotate, stars orbit the center. If the stars are moving in a spiral pattern, then obviously the spiral is rotating too. Obvious, simple, wrong. The breakthrough came in the 1960s when a Swedish astronomer named Bertil Lindblad and later two American astrophysicists named Chia Lin and Frank Chu developed what is now called density wave theory. The theory was radical at the time. It said that spiral arms are not made of matter moving together in formation. They are regions of higher density that move through the disk at their own speed, independent of the stars and gas. The stars do not stay in the arms. They pass through them, the way cars pass through a traffic jam on a highway. That analogy is the key to understanding the whole thing, so let us start there. Picture yourself driving on a highway. Traffic is moving smoothly at 70 miles per hour. Then up ahead you see brake lights. A clump of cars has formed. A slow-moving section of the highway where everyone is doing 40 instead of 70. You do not know why. Maybe there was an accident that has since cleared. Maybe someone hit the brakes for no reason and caused a ripple. It does not matter. The clump is there. You reach the clump, you slow down, you spend a few minutes crawling along at 40 miles per hour surrounded by other cars, and then the road opens up again and you accelerate back to 70. You have passed through the traffic jam, but the traffic jam itself has not moved with you. It is still sitting in the same stretch of highway, slowing down the next group of cars that arrives from behind. The jam persists even though the cars inside it are constantly changing. New cars enter from the back, slow down, then leave from the front. The density of cars in that section of the highway is higher than the surrounding road, but the individual cars are not stuck there. They pass through. Spiral arms work exactly the same way. M51 is a rotating disk of stars and gas. Every star in the disk is on its own orbit around the galactic center, moving at a speed determined by how far it is from the core and how much mass is pulling on it. Stars closer to the center orbit faster. Stars farther out orbit slower. This is the same reason Mercury orbits the Sun faster than Earth, and Earth orbits faster than Jupiter. Gravity weakens with distance, so objects farther out take longer to complete one lap. In a galaxy, this creates what astronomers call differential rotation. The disk does not spin like a solid plate, it shears. The inner parts rotate faster than the outer parts, and the result is that the disk stretches and twists over time like dough being kneaded. Now add a density wave. A density wave is a region where the gravitational field of the disk has a slight overdensity, a bump in the otherwise smooth distribution of matter. That bump creates a gravitational pull that is slightly stronger than the surrounding regions. As stars orbit the galaxy, they feel that pull. When a star approaches the wave, it slows down slightly, like a car approaching a traffic jam. It spends some time moving through the wave at a reduced speed, then exits on the other side and speeds back up to its normal orbital velocity. The wave itself is not moving at the same speed as the stars. It has its own rotation rate, called the pattern speed, which is slower than the stars in the inner disk and faster than the stars in the outer disk. The result is that stars are constantly entering and leaving the wave, but the wave persists because new stars are always arriving to replace the ones that leave. The density wave in M51 takes the form of two spiral arms. The wave is not a physical object. It is a pattern in the gravitational field of the galaxy, a standing wave that rotates at a fixed speed while the stars and gas move through it. The arms look bright because the density wave compresses the gas. When a cloud of hydrogen gas drifts into a spiral arm, the increased gravitational pull from the wave squeezes the cloud, raising its density. If the cloud gets dense enough, it collapses under its own gravity and ignites into new stars. Those stars are hot, blue, and bright, and they light up the spiral arm like a neon sign. But the stars do not stay in the arm forever. They continue on their orbits, drifting out of the wave and into the space between the arms. By the time they leave, many of the massive blue stars have already died. They only live for a few million years, which is a blink of an eye in galactic terms. The arm stays bright because new stars are constantly forming inside it, a conveyor belt of birth that has been running for hundreds of millions of years. This is why the spiral arms of M51 are blue and pink. Blue from the young massive stars that are burning through their fuel at a ferocious rate. Pink from the ionized hydrogen gas surrounding those stars, heated to tens of thousands of degrees by the ultraviolet radiation pouring out of the stellar surfaces. Every pink patch you see in an image of the Whirlpool is a region where stars are being born right now. Not metaphorically, right now. This second. As you are reading this, clouds of hydrogen in M51 spiral arms are collapsing under their own weight, heating up, igniting fusion in their cores, and beginning to shine. The process takes a few 100,000 years from start to finish, which sounds like a long time until you remember that the light we are seeing left M51 23 million years ago. The stars that are forming in the arms right now, in the galaxies present, will not be visible from Earth for another 23 million years. What we see when we look at M51 is history. The galaxy we are observing is frozen in the past, a snapshot of what the Whirlpool looked like when saber-toothed cats were prowling the plains of Africa. Density wave theory answered a question that had been bothering astronomers for decades. If spiral arms were material structures rotating with the disk, they should wind up over time. The inner parts of the disk rotate faster than the outer parts, so any pattern embedded in the disk would get stretched and twisted until it became a tight spiral with dozens of arms wrapped around the core like a ball of yarn. But that is not what we see. Most spiral galaxies have 2 or 3 or 4 arms at most, and those arms maintain a relatively open structure over billions of years. The winding problem, as it was called, was a major puzzle. Density wave theory solved it by decoupling the arms from the stars. If the arms are waves rather than material structures, they do not wind up. The wave rotates at a fixed pattern speed, and the stars move through the wave without dragging it along. The pattern persists because the wave is continuously reinforced by the gravitational field of the disk. The collision with NGC 5195 plays a key role in setting up the density wave in M51. Tidal forces from the companion galaxy during the close pass created a disturbance in the outer disk, a gravitational ripple that propagated inward like a wave moving across the surface of a pond. That ripple became the density wave, and the wave organized the gas and stars into the two dominant spiral arms we see today. Without the collision, M51 might have had spiral arms, but they would have been weaker and less symmetric. The interaction amplified the wave, turning the whirlpool into a grand design spiral. The arms are not being pulled into shape by NGC 5195 directly. The companion triggered the wave, but the wave is now self-sustaining, maintained by the internal dynamics of the disk. The pattern speed of the spiral arms in M51 has been measured. Astronomers do this by tracking the motion of gas clouds and star clusters at different distances from the center and comparing their velocities to the rotation rate of the spiral pattern. The arms rotate at about 15 kilometers per second slower than the stars in the inner disk, and about 15 kilometers per second faster than the stars in the outer disk. That difference in speed is what allows the wave to persist. If the arms rotated at the same speed as the stars everywhere in the disk, they would wind up. If they rotated much faster or much slower, the arms would either lead or trail the stars so aggressively that the pattern would fall apart. The pattern speed sits in a sweet spot, slow enough to let stars pass through but fast enough to maintain coherence. There is a special region in the disk called the corotation radius, where the stars and the spiral pattern rotate at exactly the same speed. At that radius, a star entering a spiral arm would never leave. It would stay inside the arm indefinitely, moving along with the wave. Inside the corotation radius, stars are moving faster than the pattern, so they enter the arms from behind and exit from the front. Outside the corotation radius, stars are moving slower than the pattern, so the arms overtake them from behind and leave them behind as the wave moves on. The corotation radius in M51 sits somewhere in the middle of the disk, though the exact location depends on the details of the mass distribution and the strength of the wave. Most of the visible spiral structure lies inside the corotation radius, which means most of the stars in the arms are moving faster than the pattern and passing through from back to front. The density wave also explains why the arms are star formation factories. Compression is the key. When a cloud of hydrogen gas enters a spiral arm, the increased gravitational pull from the wave squeezes the cloud, raising its density. If the cloud was already close to the threshold for gravitational collapse, the compression from the wave can push it over the edge. The cloud fragments into smaller clumps. Each clump collapses under its own gravity, and stars ignite. The process is not gentle. The compression from the density wave triggers a cascade of collapse that can turn a single large cloud into a cluster of hundreds or thousands of stars. These clusters are visible in images of M51 as bright blue knots scattered along the spiral arms. Each knot is a stellar nursery, a region where an entire generation of stars has been born in the last few million years. The gas does not stay compressed forever. After passing through the spiral arm, the gas cloud exits the wave and expands back to its original density. If star formation was triggered during the passage through the arm, the newborn stars continue on their orbits, drifting out of the arm and into the space between the arms. By the time they reach the next arm, hundreds of millions of years later, many of the stars will have aged and cooled. The massive blue stars, which dominate the light output of the young clusters, will have exploded as supernovae. What remains are longer-lived stars, yellow and red stars, that burn their fuel more slowly. The space between the arms is not empty. It is full of older stars that were born in previous passages through the spiral arms and are now drifting through the disk on their long, slow orbits around the galactic center. The traffic jam analogy holds up remarkably well when you dig into the details. In a real highway traffic jam, the density of cars is higher because cars are moving through that section of the road more slowly. The same is true in a spiral arm. The density of stars and gas is higher because everything is moving through the arm more slowly than it moves through the rest of the disk. The slowdown is not dramatic. Stars do not come to a halt inside the arm. They just decelerate slightly, spend some time at a reduced orbital velocity, then speed back up. But that slight slowdown is enough to pile up material and create the visible structure we call a spiral arm. The arm is not a thing, it is a traffic jam, a cosmic traffic jam that has been running for hundreds of millions of years. One of the predictions of density wave theory is that the spiral pattern should trigger not just star formation, but also shocks in the gas. When gas enters a spiral arm, it is moving faster than the pattern speed. As it hits the wave, it slows down abruptly, creating a compression front where the gas piles up. That compression front is called a shock, and it shows up in observations as a sharp boundary between the low-density gas outside the arm and the high-density gas inside it. Radio telescopes tuned to the emission lines of hydrogen and carbon monoxide can map these shocks in detail. In M51, the shocks are visible as narrow lanes running along the inner edge of each spiral arm, marking the boundary where gas enters the wave and compresses. The star formation happens just downstream of the shock, in the regions where the gas has been squeezed hard enough to collapse. The sequence is shock first, compression second, star formation third. The spiral arm is not just a region where stars are born. It is a factory with an assembly line. The density wave also affects the dust. Dust grains, tiny particles of carbon and silicates, are mixed in with the gas throughout the disk. When the gas compresses in a spiral arm, the dust compresses with it. The result is that the spiral arms are dusty, filled with dark lanes of obscuring material that block the light from stars behind them. Images of M51 in visible light show these dust lanes clearly, dark filaments running along the inner edge of each arm. The dust is not just a nuisance. It plays a role in star formation by shielding the gas from ultraviolet radiation, allowing molecular clouds to cool and collapse without being heated and dispersed by nearby stars. The dust also absorbs starlight and re-emits it in the infrared, which is why infrared images of M51 look different from visible light images. In the infrared, the spiral arms glow brightly with the heat of the dust, while the stars themselves are less prominent. The density wave is not a perfect, rigid pattern. It has structure, and it evolves over time. The arms can develop kinks and spurs, short segments that branch off from the main spiral and extend into the space between the arms. These features are visible in high-resolution images of M51, and they are a sign that the density wave is interacting with the gas in complicated ways. The kinks form when the gas flow through the wave is not smooth, when turbulence or feedback from star formation disrupts the compression front and causes the gas to pile up in unexpected places. The spurs are temporary. They last for a few tens of millions of years before fading as the gas disperses and the wave re-establishes its regular pattern. But they are a reminder that the spiral arms are not static. They are dynamic, constantly being shaped by the flow of gas and the gravitational forces acting on the disk. The density wave also has a finite lifetime. It is not a permanent feature of the galaxy. Over hundreds of millions of years, the wave can decay as energy is radiated away through gravitational interactions with the stars and gas. In some galaxies, the spiral arms fade over time, leaving behind a smooth, featureless disk with no clear structure. In other galaxies, new waves are triggered by fresh disturbances, collisions with other galaxies, or the infall of gas from the intergalactic medium. M51 is in the middle of this cycle. The wave was triggered by the collision with NGC 5195, and it is still strong today, but eventually the wave will weaken unless another interaction comes along to reinforce it. The Whirlpool's perfect spiral arms are temporary, a brief moment in the long history of the galaxy when the conditions were just right for a grand design pattern to emerge. The fact that spiral arms are density waves rather than material structures was not immediately accepted when Lindblad and Lin and Shu first proposed it. The idea felt too abstract, too disconnected from the physical reality of stars and gas. It took years of observational work to confirm the predictions of the theory. Radio telescopes mapped the motion of gas clouds in nearby spiral galaxies and found that the gas was indeed slowing down as it entered the arms and speeding up as it left. Optical telescopes tracked the ages of star clusters along the spiral arms and found that the youngest clusters were concentrated near the inner edge of the arms, exactly where the density wave theory predicted they should form. Infrared telescopes measured the distribution of dust and confirmed the presence of shock fronts along the leading edge of each arm. One by one, the predictions were verified, and density wave theory became the standard explanation for how spiral arms work. M51 played a central role in this process. The galaxy is close enough and bright enough and face-on enough that astronomers could study its spiral arms in detail. The two dominant arms made it an ideal test case for the theory. If density waves were real, they should show up most clearly in grand design spirals like the Whirlpool. And they did. Every observation matched the theory. The arms were regions of higher density, the gas was compressed, the star formation was triggered by the compression, the pattern rotated at a fixed speed, the stars and gas moved through the pattern, the traffic jam analogy held. M51 became the poster child for density wave theory, the galaxy that proved the arms are waves. There are still details that are not fully understood. The exact mechanism that maintains the wave over long timescales is an area of active research. Some models suggest that the wave is continuously driven by the gravitational influence of the companion galaxy, even now, millions of years after the initial pass. Other models propose that the wave is self-sustaining, maintained by the internal dynamics of the disk without needing external reinforcement. The truth is probably somewhere in between. The collision with NGC 5195 triggered the wave, but the wave is now being shaped by the ongoing tidal interaction as the two galaxies continue their slow waltz. The final chapters of that interaction have not yet been written. What is clear is that the spiral arms of M51 are not what they appear to be. They are not solid. They are not rotating as rigid structures. They are not made of the same stars and gas over time. They are patterns, waves in the gravitational field of the galaxy, moving through the disk at their own pace, while the stars and gas pass through them like cars through a traffic jam. The arms look permanent because the wave is persistent, but the material inside the arms is always changing, always flowing, always being replaced by new stars and new gas drifting in from behind. The spiral structure you see in images of the Whirlpool is a snapshot of a process that has been running for hundreds of millions of years and will continue running for hundreds of millions more. The arms are not a thing. They are a verb. They are the galaxy in the act of organizing itself, compressing its gas, forming its stars, building its structure one density wave at a time. And inside those waves, in the compressed lanes of gas and dust where the density peaks and the gravitational pull is strongest, something is happening right now that is older than mountains and faster than thought. Stars are being born. Whole clusters of them igniting in the dark, flooding the spiral arms with light. That is where the story goes next. The arms are doing something, not just compressing gas, not just creating density waves, not just organizing the flow of material through the disk. They are building stars. Right now, as you sit in your chair reading these words, deep inside the spiral arms of the Whirlpool Galaxy, clouds of hydrogen are collapsing under their own weight, heating up, igniting fusion in their cores, and beginning to shine. The process takes a few 100,000 years from start to finish, which sounds like forever, until you remember that the light we are seeing left M51 23 million years ago. The stars being born in those arms right now, in the galaxy's present, will not be visible from Earth for another 23 million years. What we see when we look at the whirlpool is history. A snapshot of the galaxy as it was when our planet was young and our ancestors had not yet learned to walk upright. And in that snapshot, frozen in time, the spiral arms are on fire. The blue regions are where the action is. In every high-resolution image of M51, in every Hubble photograph and every Kit peak exposure, and every composite assembled from dozens of wavelengths, the spiral arms glow with bright knots of blue light scattered along their length like beads on a string. Those knots are not individual stars, they are clusters. Entire neighborhoods of newborn suns, hundreds or thousands of them packed into regions only a few dozen light-years across. The blue color comes from the stars themselves. Hot, massive, young stars burn blue. They are the kind of stars that live fast and die hard, pouring out energy at a rate that makes our sun look like a dying candle. A single blue supergiant can shine with the light of 100,000 suns. Pack a few thousand of them into a cluster, and the whole region lights up like a flare, bright enough to be visible across millions of light-years of intergalactic space. That is what we are seeing when we look at the blue strands in M51. We are seeing the galaxy in the act of building itself, one generation of stars at a time. The raw material for all those stars is hydrogen. The universe is made mostly of hydrogen, always has been. When the Big Bang happened 13.8 billion years ago, the first atoms that formed were hydrogen and helium and traces of lithium, nothing else. No carbon, no oxygen, no iron, no silicon, just the simplest elements, the ones that could assemble themselves in the heat of the early universe. Everything heavier than lithium had to be built inside stars, forged in the nuclear furnaces at their cores, and then scattered back into space when the stars died. But hydrogen was there from the beginning. It is the feedstock, the building block, the universal raw material from which everything else is made. And in the spiral arms of M51, hydrogen is everywhere. Vast clouds of it, drifting through the disk, waiting for something to push them over the edge into collapse. That something is gravity. Gravity is patient. It does not care how long it takes. It just pulls, constantly, inexorably, on every atom in the cloud. If the cloud is small and diffuse, gravity loses. The thermal motion of the atoms, the random jiggling of particles bouncing off each other, is enough to counteract the pull. The cloud stays stable, drifting through space, never collapsing. But if the cloud is large enough and dense enough, gravity wins. The pull from all the atoms in the cloud combines into a force strong enough to overcome the thermal pressure, and the cloud begins to fall inward on itself. Slowly at first, then faster. The collapse is not uniform. The cloud fragments into smaller clumps as it falls, each clump pulling itself together under its own gravity. Within a few 100,000 years, the cloud has shattered into dozens or hundreds or thousands of individual cores, each one destined to become a star. This is where the density waves come back into the story. The spiral arms are density waves, regions where the gravitational field of the galaxy is slightly stronger than the surrounding disk. When a hydrogen cloud drifts into a spiral arm, the wave compresses it. The compression raises the density, which strengthens the gravitational pull, which speeds up the collapse. Clouds that were stable outside the arm become unstable inside it. The density wave is a trigger. It takes clouds that were sitting on the edge of collapse and pushes them over. That is why the spiral arms of M51 are packed with star formation. It is not that the arms contain more gas than the rest of the disk. It is that the gas inside the arms is being squeezed hard enough to collapse. The arms are not just regions of higher density, they are regions where the conditions are right for gravity to win. Astronomers call these collapsing clouds stellar nurseries. The term is apartment A nursery, is a place where new life begins, where fragile things are kept safe until they are strong enough to survive on their own. A stellar nursery is a place where new stars are born, where clouds of hydrogen collapse and heat up and ignite fusion and begin their long, slow burn through billions of years of existence. The nurseries in M51 are enormous. The largest of them span hundreds of light years, contain millions of solar masses worth of gas, and are actively forming thousands of stars at once. They are not quiet, they are not gentle. They are chaotic, violent, turbulent regions where gravity and pressure and radiation and magnetic fields are all fighting for control. The process of star formation is messy. It is not a smooth collapse. It is a battle. The gas inside a stellar nursery is not pure hydrogen. It is mostly hydrogen, about 70% by mass, with helium making up most of the rest, and a tiny fraction of heavier elements mixed in. Carbon, oxygen, nitrogen, iron, silicon, all the stuff that was built inside previous generations of stars and then ejected into space when those stars died. The heavy elements do not contribute much to the mass, but they contribute enormously to the physics. They allow the gas to cool. Hydrogen is lousy at radiating away energy. It has only a few transitions, a few specific wavelengths at which it can emit light, and most of those require the gas to be very hot. But heavier elements have dozens or hundreds of transitions. They can radiate energy at lower temperatures, pulling heat out of the gas and allowing the cloud to collapse further. Without heavy elements, star formation would be much harder. The clouds would stay hot and puffy, unable to compress enough to trigger collapse. The presence of even a tiny amount of carbon or oxygen makes the whole process easier. M51 has been forming stars for billions of years, and every generation of stars has enriched the gas with heavier elements. The stellar nurseries in the Whirlpool today are easier to ignite than the nurseries in the early universe, when the gas was pristine and metal-free. Inside the collapsing cloud, the temperature is rising. As the gas falls inward, gravitational potential energy is converted into kinetic energy. The atoms are moving faster, colliding more often, heating up. At first, the heat escapes, the cloud radiates away the energy as infrared light, cooling itself and allowing the collapse to continue. But as the cloud gets denser, the heat has a harder time escaping. The gas becomes opaque, trapping the thermal radiation inside. The temperature climbs, the pressure builds, the collapse slows. At the center of each collapsing core, a protostar begins to form. This is not yet a star. It is a hot, dense ball of gas that is still pulling in material from the surrounding cloud. It is glowing, But the glow comes from the heat of the collapse, not from fusion. Fusion requires temperatures of at least 10 million degrees Kelvin. The core of a protostar is not there yet. It is only a few thousand degrees, maybe 10,000 if the collapse is fast. The protostar is a baby. It is not yet burning its fuel. It is just getting ready. The protostar phase lasts for a few 100,000 years. During that time, the protostar continues to grow, pulling in more gas from the surrounding cloud. The infalling material does not land gently. It crashes into the surface of the protostar at high speed, releasing energy as heat and light. The protostar glows brightly in the infrared, but it is hidden inside a thick cocoon of dust. Visible light cannot escape. The dust absorbs the starlight and re-emits it at longer wavelengths. An infrared telescope looking at a stellar nursery sees hundreds or thousands of bright spots, each one a protostar buried inside a collapsing cloud. An optical telescope sees almost nothing, just dark patches where the dust is blocking the light. The birth of a star is hidden from view, but eventually the core gets hot enough. When the temperature at the center of the protostar reaches about 10 million degrees Kelvin, hydrogen nuclei start slamming into each other with enough energy to overcome the electromagnetic repulsion between their positively charged protons. They fuse. Two hydrogen nuclei combine to form helium, releasing a tiny burst of energy in the process. Each individual fusion reaction releases almost nothing. A fraction of a fraction of a fraction of the energy you would get from burning a single match. But there are trillions upon trillions upon trillions of reactions happening every second. The combined energy output is enormous. The core of the protostar suddenly has a new source of heat, a furnace that will keep burning for billions of years as long as there is hydrogen to fuel it. Fusion ignites. The protostar becomes a star. The transition is not dramatic. There is no explosion, no sudden flash. The star just starts to shine more steadily, powered now by fusion instead of collapse. The infalling gas slows and eventually stops as the radiation pressure from the newborn star pushes back against the weight of the surrounding cloud. The cocoon of dust begins to clear as the star's ultraviolet light heats the material and drives it away. Within a few million years, the star emerges from its birthplace, visible for the first time in optical light. It has reached the main sequence, the long stable phase where it will spend the majority of its life burning hydrogen into helium in its core. Our Sun is a main sequence star. It has been burning steadily for 4.6 billion years and will continue for another 5 billion before it runs out of fuel. The stars being born in M51 today will follow the same path, though the massive ones, the blue supergiants, will burn out much faster. The stellar nurseries in M51 are visible because they contain not just protostars, but fully formed young stars that have already ignited. The massive stars, the ones that burn blue and hot, do not wait around. They light up within a few million years of starting their collapse, and once they ignite, they flood the surrounding gas with ultraviolet radiation. That radiation is powerful enough to ionize hydrogen, stripping electrons off the atoms and leaving behind a plasma of free protons and electrons. The ionized gas glows in a specific shade of red, the color of hydrogen alpha emission, the same color you see in pictures of nebulae like the Orion Nebula or the Eagle Nebula. In images of M51, the pink regions scattered along the spiral arms are H2 regions, clouds of ionized hydrogen surrounding clusters of newborn stars. The pink glow is a direct signature of star formation. Everywhere you see pink, stars have recently been born. The H2 regions in M51 are enormous. The largest of them span hundreds of light years and contain enough ionized gas to make thousands of solar masses. They are not smooth. They are filamentary, threaded with dark lanes of dust and bright knots of emission where the gas is particularly dense. The ultraviolet light from the central stars is not just ionizing the gas, it is also heating it to tens of thousands of degrees and driving it outward in a wind that gradually disperses the cloud. The H2 region is temporary. It will last for a few million years, long enough for the massive stars at the center to burn through their fuel and explode as supernovae. After that, the gas will cool and recombine, the glow will fade, and the region will disappear. But while it lasts, it is spectacular, a beacon of star formation visible across the galaxy. The process does not stop with the first generation of stars. Once the massive stars ignite and start pumping out radiation, they begin to reshape the surrounding cloud. The ultraviolet light heats the gas, creating pressure that pushes back against the infall. The radiation also drives a wind, a stream of particles blown outward from the star's surface at hundreds of kilometers per second. The wind carves out a bubble in the cloud, a cavity where the gas has been cleared away, and the star sits in the center like a pearl in an oyster. The edges of the bubble are bright, glowing with the light of the ionized gas. And at those edges, the compression from the expanding bubble can trigger a new round of collapse. New protostars form in the compressed gas, igniting their own fusion reactions, creating their own bubbles, triggering yet more collapse. The process cascades. One generation of stars triggers the next, and the next, and the next. A single stellar nursery can produce multiple generations of stars over the course of tens of millions of years, each generation reshaping the cloud and setting the stage for the next. The feedback from massive stars is not just radiation and wind, it is also supernovae. Massive stars, the kind that dominate the light output of stellar nurseries, live for only a few million years before they run out of fuel. When that happens, the core collapses and the outer layers explode in a supernova, one of the most violent events in the universe. A single supernova releases as much energy in a few seconds as the sun will emit over its entire 10 billion year lifetime. The explosion sends a shockwave tearing through the surrounding gas at thousands of kilometers per second, compressing everything in its path. That compression can trigger yet another round of star formation, seeding new protostars in the debris of the old. But the shockwave also destroys. It heats the gas to millions of degrees, too hot to collapse. It disperses the cloud, blowing it apart and scattering it across hundreds of light years. The stellar nursery that gave birth to the star is ripped to pieces by the star's death. The life cycle is brutal. Birth, life, death, and in the debris of death, the seeds of new birth. The Chandra X Ray Observatory has mapped M51 in high-energy light, and the picture it reveals is one of violence. The galaxy is full of X-ray sources, hundreds of them, scattered across the disk and concentrated in the spiral arms. Most of those sources are the remnants of dead stars. Neutron stars and black holes left behind after supernovae, still glowing with the heat of their formation, or pulling in gas from companion stars and heating it to millions of degrees. The diffuse X-ray emission, the faint glow that fills the spaces between the bright point sources, comes from hot gas heated by supernova shockwaves. The spiral arms of M51 are not just star formation factories. They are graveyards. Every bright blue cluster you see in an optical image will someday explode, and when it does, it will leave behind a hot bubble of X-ray emitting gas that will persist for millions of years before cooling and fading. The scale of star formation in M51 is staggering. The galaxy contains over 100 billion stars, and most of them were born in the spiral arms, in stellar nurseries that have long since dispersed. The current generation of star formation is producing new stars at a rate of a few solar masses per year. That might not sound like much. Our Sun is one solar mass, so M51 is building a few new suns every year. But multiply that rate by 1 billion years, and you get billions of solar masses worth of new stars. The spiral arms have been active for hundreds of millions of years, cycling gas through the density waves, compressing it, igniting it, dispersing it, and starting the process over again. The whirlpool is not a static object. It is a machine, a factory that has been running for longer than continents have existed on Earth, building stars out of hydrogen and enriching the galaxy with the debris of their deaths. The interaction with NGC 5195 has amplified the process. The collision funneled extra gas into the disk, increasing the density and making it easier for clouds to collapse. The tidal forces from the companion triggered the density waves that organized the spiral arms, creating the conditions for sustained star formation over tens of millions of years. Without that interaction, M51 would still be forming stars. Spiral galaxies do that naturally. But the star formation rate would be lower, the arms would be weaker, and the galaxy would not look the way it does. The collision turned the whirlpool into a showcase. It made the spiral arms brighter, the H2 regions larger, the stellar nurseries more active. The beauty of M51 is a direct consequence of the violence of the collision. There is a question that keeps coming up in the literature. How long can this last? How long can M51 keep forming stars at this rate before it runs out of gas? The answer depends on how much gas the galaxy has and how efficiently it is converting that gas into stars. Estimates suggest that M51 contains several billion solar masses of hydrogen spread across its disk. At the current star formation rate, that gas will last for a few billion years, maybe longer if the rate slows down. But the interaction with NGC 5195 is ongoing. The two galaxies are still pulling on each other, still exchanging material, still reshaping each other's structure. When they finally merge, a few 100 million years from now, the collision will trigger an even more intense burst of star formation, a starburst that will consume much of the remaining gas in a relatively short time. The merger will transform M51 from a grand design spiral into something else, probably an elliptical galaxy, a featureless blob of old stars with no spiral arms and no ongoing star formation. The stellar nurseries we see today will be gone. The blue clusters will fade and die. The H2 regions will disperse. The whirlpool will become a relic, a galaxy that was once beautiful and is now just old. But that is millions of years in the future. For now, the fires are still burning. The spiral arms are still glowing. The stellar nurseries are still collapsing, igniting, exploding, collapsing again. The process is relentless. Every second, somewhere in the whirlpool, a protostar is reaching the temperature threshold for fusion and beginning to burn. Every minute, a new cluster of stars is lighting up an H2 region and flooding the surrounding gas with ultraviolet light. Every day, a massive star somewhere in the galaxy is exploding as a supernova, sending a shockwave tearing through a stellar nursery and triggering the birth of the next generation. The life cycle runs on a timescale that makes human history look like a sneeze. Empires rise and fall, species evolve and go extinct, continents drift and collide, and the whole time, 23 million light-years away, the whirlpool is forming stars. The images we have of M51 are snapshots of that process, frozen moments in the long continuous story of a galaxy building itself. The blue clusters are the newborns, stars that ignited within the last few million years and are still burning hot and bright. The pink H2 regions are the nurseries, the places where stars are being born right now. The yellow core is the retirement home, packed with older stars that were born billions of years ago and have long since settled into quiet middle age. And the dark lanes threading through the spiral arms are the raw material, the dust and gas that will someday collapse and ignite and join the ranks of the newborns. Every part of the galaxy is at a different stage of the life cycle. Birth, life, death, and rebirth, all happening at once, all visible in the same image. There is something almost miraculous about the fact that we can see this at all. 23 million light-years is an unfathomable distance. The light reaching our telescopes left M51 when the Earth was unrecognizable, when the continents were in different positions, when the ancestors of every living thing on this planet were unimaginably different from what they are now. And yet we can resolve individual stellar nurseries. We can map the spiral arms. We can identify clusters of newborn stars and measure their ages and calculate how fast they are forming. The technology we have built, the Hubble Space Telescope and the Chandra X Ray Observatory and the James Webb Space Telescope and a dozen others, has given us the ability to watch the universe in the act of creating itself, to see stars being born across millions of light-years of space, to trace the life cycle from collapsing cloud to glowing protostar to main sequence star to supernova remnant. To understand not just what M51 looks like, but how it works. And the stars being born in those nurseries today, the blue supergiants and the red dwarfs and everything in between, are not going to look the same forever. The massive ones, the blue giants that dominate the light output of the spiral arms, are already doomed. They are burning through their fuel so fast that they will be dead long before our sun reaches middle age. They are the brightest stars in the galaxy, the ones that light up the H2 regions and carve out the bubbles and trigger the cascades of star formation. They are also the shortest lived. A few million years of glory, and then they explode. The life cycle of a massive star is a sprint, not a marathon. And that sprint, that brief, furious burn, is what we turn to next. They do not last. That is the first thing you need to know about the blue supergiants scattered through the spiral arms of the Whirlpool Galaxy. They are the brightest objects in M51, the stars that dominate every photograph, the brilliant blue knots that light up the spiral arms like neon signs. They are massive, hot, luminous beyond any reasonable scale. A single blue supergiant can outshine 100,000 suns. They flood the surrounding space with enough ultraviolet radiation to ionize clouds of hydrogen the size of solar systems. They are the engines of star formation, the sources of heavy elements, the architects of galactic structure, and they are already dying, not metaphorically, not eventually, right now. Every blue supergiant you see in an image of M51 is burning through its fuel so fast that it will be dead in a cosmological eye blink. The timescale for these stars is not billions of years, it is tens of millions, maybe less. They live fast, burn bright, and explode. And when they explode, they reshape the galaxy around them in ways that will echo for millions of years after they are gone. Let us start with what a blue supergiant actually is. The term is descriptive. Blue because the star is hot enough that most of its light comes out in the blue and ultraviolet end of the spectrum. Supergiant because the star is enormous, hundreds of times larger than our sun in some cases. These are not average stars, they are the upper end of the mass distribution, the heavyweights, the monsters. A blue supergiant typically weighs somewhere between 20 and 100 solar masses. Some are even larger. The exact mass depends on how the star formed, how much gas it pulled in during its protostar phase, and whether it was born alone or in a crowded cluster where interactions with other stars could strip away part of its envelope. But the key point is that these stars are massive. Mass is destiny in the life of a star. It determines how hot the core gets, how fast the fusion reactions run, how brightly the star shines, and how long it lasts. Massive stars do everything faster. They ignite faster, they burn faster, they die faster. A star like our Sun will burn hydrogen in its core for about 10 billion years. A blue supergiant burns through its hydrogen in a few million. The reason is simple. More mass means more gravity. More gravity means more pressure in the core. More pressure means higher temperatures. Higher temperatures mean faster fusion. The fusion rate is not linear with temperature. It is exponential. Double the core temperature and the fusion rate does not double. It goes up by a factor of 10 or 100 or more, depending on which fusion reactions are running. A blue supergiant has a core temperature of tens of millions of degrees, much hotter than the 15 million degrees at the center of the Sun. The fusion reactions in the core are running at a furious pace, converting hydrogen into helium at a rate that would drain the Sun's entire fuel supply in a few thousand years. The energy output is staggering. A typical blue supergiant has a luminosity of 100,000 solar luminosities or more. Some reach 1,000,000. They are the brightest stars in the galaxy, outshining entire clusters of smaller stars. That brightness comes at a cost. Energy is being generated in the core through fusion, and that energy has to get out somehow. In smaller stars like the Sun, energy is transported outward by radiation and convection. Photons bounce around inside the star, slowly working their way from the core to the surface, a journey that takes tens of thousands of years. In massive stars, the energy output is so high that radiation alone cannot carry it all. The outer layers of the star become unstable, churning and boiling in massive convective cells that transport heat from the core to the surface much faster than radiation can. The result is a star that is constantly shedding mass. Blue supergiants have powerful stellar winds, streams of particles blown off the surface at hundreds or even thousands of kilometers per second. The wind is so strong that a blue supergiant can lose a significant fraction of its mass over the course of its lifetime, sometimes shedding tens of solar masses worth of material into the surrounding space. That material does not disappear. It becomes part of the interstellar medium, the diffuse gas and dust that fills the spaces between stars. And because the star has already started fusing heavier elements in its core, that ejected material is enriched with carbon, nitrogen, oxygen, and other elements that were not present in the original hydrogen cloud. The stellar wind is the first way a massive star gives back to the galaxy. The life cycle of a blue supergiant is short but eventful. The star begins its life as a main sequence star, burning hydrogen in its core and shining steadily. For a star this massive, the main sequence phase lasts only a few million years. During that time, the core is converting hydrogen into helium, building up a helium-rich core surrounded by a hydrogen-burning shell. When the hydrogen in the core runs out, the core contracts and heats up. The temperature rises until it is hot enough to ignite helium fusion. Helium nuclei, which are much harder to fuse than hydrogen, require temperatures of about 100 million degrees. Once that threshold is reached, the core starts burning helium into carbon and oxygen. The star swells, the outer envelope expands, and the surface cools slightly, though not enough to make the star stop being blue. The star has entered the supergiant phase. It is now larger, brighter, and closer to the end of its life. Helium burning does not last long, a few 100,000 years at most. The helium in the core is consumed much faster than the hydrogen was because the energy output is even higher. When the helium runs out, the core contracts again. The temperature climbs, carbon fusion ignites, then neon, then oxygen, then silicon. Each stage produces heavier elements and lasts for a shorter time. Carbon burning lasts a few thousand years. Neon burning lasts a few years. Oxygen burning lasts a few months. Silicon burning, the final stage, lasts about a day. At each step, the core gets smaller, hotter, denser, and the fusion reactions get faster. The star is racing toward a cliff, and at the bottom of that cliff is iron. Iron is where the process stops. Iron nuclei are the most stable nuclei in the universe. Fusing iron into heavier elements does not release energy, it absorbs energy. Once the core of a massive star starts producing iron, fusion stops being an energy source and becomes an energy sink. The core is no longer generating the outward pressure needed to hold the star up against its own gravity. The support disappears. The core collapses. Not slowly, not gradually. In less than a second, the iron core, which has been sitting at the center of the star holding everything together, implodes. The collapse is so fast that the outer layers of the star do not have time to react. The core reaches nuclear densities, the kind of densities you find inside an atomic nucleus, and the collapse halts abruptly as the core rebounds. The rebound sends a shock wave tearing outward through the star at a significant fraction of the speed of light. The shock wave hits the outer layers, which are still falling inward, and the collision releases an unimaginable amount of energy. The star explodes. This is a core collapse supernova. The explosion is one of the most violent events in the universe. For a few weeks, the dying star shines as brightly as an entire galaxy. Then it fades, leaving behind a neutron star, or a black hole at the center, and a rapidly expanding shell of gas and debris. The debris is where things get interesting. The explosion does not just destroy the star, it creates new elements. During the collapse and the explosion, the core reaches temperatures and densities high enough to forge elements heavier than iron. Gold, platinum, uranium, all the elements that cannot be made by normal fusion are created in the chaos of a supernova. The explosion scatters those elements into space, mixing them with the hydrogen and helium that were already there. The next generation of stars that forms from that enriched gas will have heavier elements built into them from the start. Rocky planets can form, life can emerge. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of calcium in your bones was forged inside a massive star and scattered into space when that star exploded. You are made of supernova debris. So is the Earth. So is everything on it. The blue supergiants in M51 are not just making light. They are making the building blocks of planets and life. The supernova also creates a shockwave that does not stop when the explosion fades. The shockwave keeps moving outward, plowing through the surrounding gas at thousands of kilometers per second. When it hits a cloud of hydrogen, it compresses the cloud, raising its density and triggering collapse. New stars form. The death of one massive star can trigger the birth of dozens or hundreds of new stars. This is called triggered star formation, and it is a major driver of star formation in spiral galaxies like M51. The density waves in the spiral arms already compress the gas, but the supernovae add an extra kick. They create localized regions of higher density where the gas is squeezed hard enough to collapse even if it was stable before. The result is a cascade. One generation of massive stars forms, ignites and explodes. The explosions trigger the next generation. That generation explodes and triggers the next. The process feeds itself, turning the spiral arms into continuous conveyor belts of birth and death. M51 is full of these explosions. The Chandra X Ray Observatory has mapped the galaxy in high-energy light and found hundreds of X-ray sources scattered across the disk. Most of those sources are supernova remnants, the expanding shells of hot gas left behind by exploded stars. The remnants glow in X-rays because the gas is heated to millions of degrees by the shock wave. A single supernova remnant can stay visible in X-rays for tens of thousands of years before it cools and fades into the background. The fact that Chandra sees hundreds of them means that supernovae are going off in M51 all the time. Not every day, maybe not every year, but often enough that the galaxy is constantly being reshaped by the explosions. The spiral arms are not just bright because of the stars being born, they are bright because of the stars dying. The feedback from supernovae is not just local. The explosions pump enormous amounts of energy into the interstellar medium, heating the gas and driving it outward in galactic winds. These winds can blow gas out of the disk entirely, ejecting it into the halo or even into intergalactic space. The process is called supernova-driven outflow, and it is one of the main ways galaxies regulate their star formation. If too many massive stars form and explode in a short time, the feedback can blow away all the remaining gas, shutting down star formation until new gas falls back in. M51 has not reached that point. The star formation rate is high, but the galaxy is not blowing itself apart. The feedback is strong enough to shape the structure of the arms and carve out bubbles in the gas, but not strong enough to stop the process entirely. The balance is delicate. Too much feedback and the galaxy goes quiet. Too little and the gas collapses too quickly, forming stars faster than the galaxy can sustain. M51 is in the sweet spot, forming stars at a rate that can continue for billions of years as long as the gas supply holds out. The interaction with NGC 5195 has amplified the process. The collision funneled extra gas into the disk, increasing the density and making it easier for massive stars to form. The tidal forces from the companion triggered the density waves that organized the spiral arms, creating the conditions for sustained star formation. The result is a galaxy that is forming blue supergiants at a higher rate than it would be if it were isolated. More blue supergiants means more supernovae. More supernovae means more feedback, more triggered star formation, more enrichment of the interstellar medium with heavy elements. The collision turned M51 into a factory for massive stars, and that factory is running at full capacity. The timescale for all of this is what makes it so striking. A blue supergiant lives for 10 or 20 or maybe 30 million years from the time it ignites on the main sequence to the time it explodes. That is a long time by human standards. It is longer than the entire history of the genus Homo, but it is a blink of an eye in the history of a galaxy. M51 has been forming stars for billions of years. The massive stars we see in the spiral arms today are not the first generation. They are not even the 10th or the 100th. They are the latest in a long continuous line of generations, each one born from the debris of the previous one, each one slightly richer in heavy elements than the one before. The blue supergiants in the Whirlpool today are not burning pure hydrogen. They are burning hydrogen that was enriched with carbon and oxygen and nitrogen by the explosions of earlier generations, and when they explode, they will enrich the gas even further, setting the stage for the next generation. The cycle has been running for so long that the interstellar medium in M51 is significantly more metal-rich than it was when the galaxy first formed. Astronomers use the term metallicity to describe the fraction of heavy elements in a star or a cloud of gas. M51 has a high metallicity compared to the early universe, and that high metallicity makes it easier for planets to form around the stars being born in the spiral arms today. The explosions also create structure. The supernova remnants do not just heat the gas, they shape it. The expanding shells carve out cavities in the interstellar medium, pushing the gas into dense shells at the edges of the remnants. Those dense shells become the sites of new star formation. The cycle is self-reinforcing. Supernova creates shell, shell collapses, new stars form, new stars explode, new shells form. The process repeats. Over time, the interstellar medium becomes a froth of overlapping shells and bubbles, each one the remnant of a supernova or a cluster of supernovae that went off in the same region. Astronomers call this the superbubble phase. Multiple supernovae in a single region combine their energy output, creating a single large bubble hundreds of light-years across. The gas inside the bubble is hot and tenuous, blown clear by the explosions. The gas at the edge of the bubble is cold and dense, compressed by the shock waves. The arms of M51 are full of these superbubbles, though they are hard to see in optical light. X-ray telescopes see them clearly. The hot gas inside the bubbles glows in X-rays, marking the locations where clusters of massive stars have already died. The blue supergiants are not evenly distributed across the galaxy. They are concentrated in the spiral arms, in the regions where the density waves have compressed the gas and triggered star formation. The space between the arms is quieter. There are stars there, older stars that were born in previous passages through the spiral arms and have since drifted into the interarm regions, but there are no blue supergiants. The massive stars do not last long enough to drift far from their birthplaces. By the time a blue supergiant exits a spiral arm, it is already near the end of its life. It explodes before it gets very far. The result is that the spiral arms are the only places in the galaxy where blue supergiants are visible. They are born in the arms, they live in the arms, and they die in the arms. Their entire existence is confined to the star formation factories where they were created. The luminosity of these stars is hard to overstate. A blue supergiant with a luminosity of 100,000 suns is pouring out energy at a rate of about 4 times 10 to the 33 watts. That is 4 followed by 33 zeros. The sun puts out about 4 times 10 to the 26 watts, so a blue supergiant is 10 million times more luminous. If you replace the sun with a blue supergiant, Earth would be vaporized instantly. The surface would heat to thousands of degrees. The oceans would boil away. The atmosphere would be stripped. The planet would become a charred cinder orbiting a furnace. And that is not even the most luminous type of star. There are stars called hypergiants that are even brighter, reaching luminosities of 1 million suns or more. M51 probably contains a few of those as well, though they are rare. The galaxy is large enough and active enough that a handful of hypergiants should exist somewhere in the disk, burning through their fuel at an even more ferocious rate than the blue supergiants. The explosions themselves are visible from Earth, not in real time, obviously. The light from M51 takes 23 million years to reach us. So any supernova we see today actually happened 23 million years ago. But supernovae are bright enough to be detected across that distance. Several supernovae have been observed in M51 over the last few decades. Astronomers monitor the galaxy regularly, taking images every few months or every year and comparing them to previous images to look for new bright spots. When a new point of light appears, it is usually a supernova. Follow-up observations confirm the identification by measuring the light spectrum and tracking how the brightness changes over time. Different types of supernovae have different light curves, different patterns of brightening and fading. Core collapse supernovae, the kind produced by massive stars, brighten rapidly over the course of a few days, peak at a luminosity of billions of suns, then fade over several months. Type 1a supernovae, which are produced by exploding white dwarfs in binary systems, have a different light curve. They brighten more slowly and peak at a slightly different luminosity. By measuring the light curve, astronomers can tell what kind of star exploded and how far away it was. M51 is close enough that individual supernovae in the galaxy are easily visible with even modest telescopes. The galaxy has been monitored for over a century, and several supernovae have been caught in the act. Each one is a data point, a snapshot of a massive star in the final moments of its life. The observations tell us how often supernovae go off in M51, what types of stars are exploding, and how much energy each explosion releases. The rate is consistent with the star formation rate. More star formation means more massive stars, which means more supernovae. The fact that M51 is forming stars at a high rate means it is also exploding stars at a high rate. The two processes are linked. You cannot have one without the other. The neutron stars and black holes left behind by the explosions are another part of the story. When the core of a massive star collapses, it does not disappear. It compresses into a neutron star or a black hole depending on how much mass is left after the explosion. A neutron star is a ball of neutrons about 20 kilometers across, with a mass of 1 or 2 suns. The density is unimaginable. A teaspoon of neutron star material would weigh 1 billion tons. Neutron stars spin rapidly, often hundreds of times per second, and they have magnetic fields trillions of times stronger than Earth's. Some neutron stars emit beams of radiation from their magnetic poles, and if one of those beams sweeps across Earth, we see a pulse of light once per rotation. We call those objects pulsars. Chandra has detected dozens of neutron stars in M51, most of them in the spiral arms where the supernovae went off. Some are pulsars, some are accreting matter from companion stars, heating the infalling gas to millions of degrees and glowing in X-rays. Each one is the remnant of a blue supergiant that exploded millions of years ago. If the core is massive enough, even the pressure from neutrons cannot hold it up. The core collapses past the neutron star stage and becomes a black hole. A stellar mass black hole weighs a few times the mass of the Sun and has an event horizon only a few kilometers across. It is not a supermassive black hole like the one at the center of the galaxy. It is much smaller, the product of a single star rather than the accumulation of millions, but it is still a black hole, a region of space where gravity is so strong that not even light can escape. Chandra has identified several stellar mass black holes in M51, mostly in binary systems where the black hole is pulling gas off a companion star. The infalling gas heats up and emits X-rays, the same way gas falling into a neutron star does. The X-ray emission is how we know the black hole is there. We cannot see the black hole directly, but we can see the light from the matter falling into it. The blue supergiants are also important for another reason. They are the sources of ionizing radiation that keep the H2 regions glowing. The pink patches scattered along the spiral arms, the regions of ionized hydrogen that mark the locations of active star formation, are all lit up by ultraviolet light from massive stars. The ultraviolet photons are energetic enough to strip electrons off hydrogen atoms, leaving behind a plasma of free protons and electrons. That plasma emits light at specific wavelengths, including the red wavelength of hydrogen alpha emission. The H2 regions are not just passive clouds of gas, they are actively being ionized and heated by the stars inside them. When the stars die, the ionization stops. The plasma recombines into neutral hydrogen, the glow fades, and the H2 region disappears. The whole structure is temporary, lasting only as long as the massive stars that power it. A few million years, and then it is gone. The enrichment of the interstellar medium is one of the most important contributions of blue supergiants to the galaxy. Every element heavier than helium was made inside a star. Some elements, like carbon and oxygen, are made in the cores of massive stars during normal fusion. Others, like gold and uranium, are made only in supernovae. The explosion disperses those elements into space, where they mix with the hydrogen and helium and become part of the next generation of stars. Over time, the metallicity of the galaxy increases. The first stars that formed in M51 billions of years ago were made of almost pure hydrogen and helium. The stars forming today contain a few percent heavy elements. That enrichment is cumulative. Every generation of massive stars adds to the total. Every supernova contributes a little more. The process has been running for so long that the gas in M51 is now rich enough in heavy elements to form rocky planets like Earth. Without the blue supergiants, without the supernovae, the galaxy would still be made of hydrogen and helium. There would be no carbon, no oxygen, no iron, no planets, no life. The spiral arms of M51 are a laboratory for studying this process. The star formation is so active and so concentrated in the arms that we can see the entire life cycle playing out in a single image. Blue supergiants lighting up the arms, H2 regions glowing pink, supernova remnants expanding outward in X-rays, neutron stars and black holes left behind by previous explosions, triggered star formation in the compressed shells at the edges of the remnants. The whole cycle is visible, frozen in the snapshot of light that left the galaxy 23 million years ago. The Whirlpool is showing us how galaxies build themselves, how they turn hydrogen into stars and stars into heavy elements and heavy elements into new stars. The process is continuous, self-sustaining, and has been running for billions of years. But the blue supergiants are not the only stars in M51 that are dying violently. There are other explosions happening, other sources of energy and feedback. And at the center of the galaxy, buried beneath the yellow glow of the core, there is something else, something much larger than any star, something that has been growing for billions of years and is still feeding today. A supermassive black hole, millions of times heavier than the blue supergiants, sitting at the gravitational heart of the Whirlpool. And that black hole, that cosmic Leviathan, has its own story to tell. At the center of the Whirlpool Galaxy, beneath layers of stars and gas and dust so thick that visible light cannot penetrate them, beneath the yellow glow of the galactic bulge and the spiral arms and the stellar nurseries and the blue supergiants burning themselves to death, there is a hole. Not a hole in the sense of empty space, not a cavity or a void or a gap, a hole in the fabric of reality itself. A region where the gravitational field is so strong that space curves inward on itself and anything that crosses the boundary never comes back. A supermassive black hole, and it is not small. Estimates put its mass at somewhere around 1 million times the mass of our Sun. Maybe more, maybe less. The exact number is hard to pin down because black holes do not emit light, and the only way to measure them is to watch how they affect the things around them. But the mass is in that range, somewhere in the millions, and that makes it a supermassive black hole by definition. Not a stellar mass black hole, the kind left behind when a massive star explodes. Not an intermediate mass black hole, the kind that might form when multiple stellar mass black holes merge. A supermassive black hole, the kind that sits at the center of almost every large galaxy in the universe and has been growing for billions of years. The existence of supermassive black holes was a surprise when astronomers first started finding evidence for them in the 1970s. Nobody expected that the centers of galaxies would be dominated by objects this massive. The math worked. General relativity, Einstein's theory of gravity, predicted that black holes could exist at any mass scale. But the idea that a single object weighing millions or billions of times the mass of the Sun could sit at the heart of a galaxy and not be immediately obvious seemed strange. Black holes are small. A black hole with 1 million solar masses has an event horizon only about 3 million kilometers across, roughly twice the distance from the Earth to the Sun. That is tiny on galactic scales. The Milky Way is about 100,000 light-years across. A supermassive black hole at the center is a speck, a point, invisible unless you know where to look. And yet they are there. Almost every galaxy has one. The Milky Way has one. Sagittarius A star, sitting at the galactic center, weighs about 4 million solar masses. Andromeda has one that weighs 100 million. The giant elliptical galaxies at the centers of galaxy clusters have black holes that weigh billions, and M51 has one too. The black hole at the center of the Whirlpool is not dormant, it is active. Not wildly active, not tearing the galaxy apart, but active enough to make its presence known. Astronomers classify M51 as a Seyfert galaxy, a type of active galaxy where the central black hole is feeding on gas and dust from the surrounding region. The feeding process generates enormous amounts of energy, more than you could ever get from normal star formation. The energy comes from the gas itself, from the gravitational potential energy that is released as the gas falls inward toward the black hole. Matter falling into a black hole heats up. It gets hot enough to glow in X-rays, hot enough to emit ultraviolet light, hot enough to ionize the surrounding gas and create visible signatures that we can detect from millions of light-years away. The black hole in M51 is not a quasar, not one of the ultra-luminous monsters that shine brighter than their entire host galaxies, but it is not quiet either. It is ticking over, accreting matter at a steady rate, pumping out energy in wavelengths we can measure. The evidence for the black hole comes from multiple sources. The most direct evidence is the motion of stars and gas near the galactic center. When you have a massive object sitting at a fixed point in space, everything around it orbits that point. The closer you get, the faster the orbital velocity. This is Kepler's third law, the same rule that governs the motion of planets around the Sun. Measure the velocity of objects near the center, measure how far they are from the center, and you can calculate how much mass is sitting at the center pulling on them. Astronomers have done this for M51 using spectroscopy, splitting the light from the galactic core into its component wavelengths and measuring how the wavelengths shift as the gas moves toward or away from us. The results show that the gas near the center is moving fast, hundreds of kilometers per second, in orbits that can only be explained by the presence of a massive compact object at the core. The mass is too high and the region is too small for it to be a cluster of stars. Stars that close together would collide and merge. The only explanation that fits the data is a supermassive black hole. The second piece of evidence is X-rays. The Chandra X Ray Observatory has observed M51 in detail, mapping the high-energy emission from the galaxy in wavelengths that visible light telescopes cannot see. The center of the galaxy glows brightly in X-rays, a clear signature of hot gas heated to millions of degrees. Gas does not get that hot by accident. You need an energy source, and the only energy source powerful enough to heat gas to those temperatures in such a small region is accretion onto a compact object. The black hole is pulling in gas from the surrounding region, and as the gas spirals inward, it forms an accretion disk. The disk is not a solid structure. It is a swirling mess of gas and dust, orbiting the black hole at speeds close to a significant fraction of the speed of light. The gas in the disk is colliding with itself, rubbing against itself, converting orbital energy into heat. The inner regions of the disk, the parts closest to the black hole, are the hottest. Temperatures reach tens of millions of degrees, hot enough that the gas emits X-rays. The X-ray glow is the calling card of an accreting black hole, and M51 has it. Chandra found nearly 500 X-ray sources scattered across M51 and its companion galaxy. Most of those sources are neutron stars and stellar mass black holes left behind by supernova explosions. But the brightest source, the one at the very center of the galaxy, is different. It is more luminous than any single stellar remnant should be. It is persistent, glowing steadily over years of observations, rather than flaring up and fading like some X-ray binaries do. And it sits at the exact gravitational center of the galaxy, the point around which everything else is orbiting. That source is the supermassive black hole. It is not the black hole itself that is glowing. Black holes do not emit light. The event horizon is a one-way boundary. Nothing that crosses it can come back, not even photons. What we are seeing is the accretion disk, the superheated gas spiraling inward, radiating its energy away in the last moments before it falls past the point of no return. The accretion process is not gentle. Gas does not fall straight into a black hole. It has angular momentum, a measure of how fast it is moving around the center. That angular momentum has to go somewhere. The gas cannot just drop straight in because the rotation prevents it. Instead, the gas settles into a disk, a flattened structure where the material orbits the black hole in roughly the same plane. The disk looks like a cosmic hurricane, a swirling vortex of gas with the black hole sitting at the eye of the storm. The gas in the disk is moving at different speeds depending on how far it is from the center. The inner edge of the disk, the part closest to the black hole, is moving at a significant fraction of the speed of light. The outer edge, farther out, is moving more slowly. The difference in speed creates friction. Gas in the inner part of the disk is moving faster than gas in the outer part, so the two layers rub against each other, generating heat. The friction is what heats the disk. The closer you get to the black hole, the hotter the disk gets. The innermost regions glow in X-rays. The outer regions, cooler and less energetic, emit ultraviolet and visible light. The whole structure is a gradient, a smooth progression from the cool outer disk to the scorching inner edge. The disk does not last forever. The gas is slowly losing angular momentum through friction and other processes that are not fully understood. As it loses angular momentum, it spirals inward, moving to smaller and smaller orbits. Eventually, it reaches the innermost stable circular orbit, the closest point to the black hole where gas can orbit without falling in immediately. That distance depends on the mass and spin of the black hole. For a non-rotating black hole, the innermost stable orbit is about 3 times the radius of the event horizon. For a rapidly spinning black hole, it can be much closer, almost touching the horizon. Inside that orbit, there are no stable paths. Any gas that crosses the innermost stable orbit is doomed. It plunges inward, crosses the event horizon in a fraction of a second, and disappears. The last bit of energy it radiates as it falls is the brightest emission we see. The innermost edge of the accretion disk, the region just outside the event horizon, is where the action is. M51 is classified as a Seyfert 2 galaxy, The Seyfert classification, named after astronomer Carl Seyfert, who first identified these objects in the 1940s, describes galaxies with bright, active nuclei that are not quite as luminous as quasars. There are two types. Seyfert 1 galaxies have broad emission lines in their spectra, indicating that we are seeing the accretion disk almost face-on, and observing gas moving at high speeds directly toward and away from us. Seyfert 2 galaxies have narrow emission lines, suggesting that we are viewing the system from an angle where the disk is partially obscured by a torus of dust and gas surrounding the black hole. The narrow lines come from gas farther out, in regions where the velocities are lower. M51 is a Seyfert 2, which means we are probably not looking straight down into the accretion disk. We are seeing it from an angle, with part of the central region hidden behind the dusty torus. That obscuration makes it harder to study the innermost parts of the system, but the X-ray emission cuts through the dust, giving us a direct view of the hot gas near the black hole. The energy output of the black hole is modest by AGN standards. Active galactic nuclei, or AGN, are systems where the central black hole is accreting matter and generating enough energy to outshine the rest of the galaxy in certain wavelengths. The most extreme AGN are quasars, where the black hole is feeding so voraciously that it can shine with the light of 1 trillion suns. M51 is nowhere near that level. The black hole is active, but it is not in a feeding frenzy. The accretion rate is relatively low, which means the energy output is relatively low. The black hole is sipping rather than gulping. That makes M51 a useful laboratory for studying moderate-level AGN activity, the kind of activity that is probably more common in the universe than the extreme quasar phase. Most supermassive black holes spend most of their time in a low-activity state, accreting small amounts of gas and producing modest amounts of radiation. The monsters, the quasars that dominate the early universe, are rare. M51 is showing us what a typical active black hole looks like when it is not at the peak of its feeding cycle. The accretion disk is not the only structure around the black hole. There is also a torus, a donut-shaped cloud of dust and gas that surrounds the disk at a larger distance. The torus is cooler and denser than the disk, and it plays a role in obscuring our view of the central region. In Seyfert 2 galaxies like M51, the torus is oriented in such a way that it blocks our direct line of sight to the innermost parts of the accretion disk. We can see the outer parts, and we can see the X-rays that punch through the dust, but the bright core is hidden. The torus also affects the spectrum of the emitted light. Dust absorbs ultraviolet and visible light from the disk, heats up, and re-emits the energy in the infrared. Infrared observations of M51 show a strong signature from the central region, consistent with a dusty torus heated by the black hole. The torus is part of the standard unified model of AGN, a framework that explains the differences between Seyfert 1 and Seyfert 2 galaxies as an orientation effect. If you look at the system from above or below, you see the disk directly and you get a Seyfert 1. If you look from the side, the torus blocks your view and you get a Seyfert 2. Same object, different viewing angle. The black hole is also affecting the gas farther out in the galaxy. Observations have revealed ionization cones, regions of gas extending outward from the nucleus in a cone-shaped pattern. The gas in these cones is ionized, meaning the atoms have been stripped of their electrons by high-energy radiation from the black hole. The ionization cones are a direct signature of the black hole's influence. The radiation from the accretion disk is so intense that it can ionize gas hundreds or even thousands of light-years away. The cones are not symmetric. They extend in two opposite directions, roughly perpendicular to the plane of the accretion disk. That geometry is consistent with radiation escaping along the rotational axis of the disk, where the obscuring torus is thinnest. The radiation travels outward, ionizes the gas, and creates the cones. The structure is similar to what has been seen in other Seyfert galaxies, and it is one of the clearest pieces of evidence that the black hole is actively feeding. The question of whether M51's black hole produces jets is more complicated. Some active galactic nuclei, particularly the most luminous ones, launch relativistic jets, narrow beams of particles accelerated to nearly the speed of light and shot outward along the rotational axis of the accretion disk. The jets can extend for millions of light years, far beyond the host galaxy, and they glow in radio wavelengths as the particles interact with the surrounding medium. Jets are powered by the rotational energy of the black hole itself, extracted through a process involving magnetic fields threading the accretion disk. Not all AGN have jets. The presence of jets seems to depend on the spin of the black hole, the strength of the magnetic field, and the accretion rate. M51 is not a strong radio source, which suggests that if there are jets, they are weak or intermittent. Radio observations have detected some emission from the nucleus, but it is not the kind of powerful jet activity you see in radio galaxies. The black hole in M51 is active, but it is not launching large-scale jets that reshape the galaxy. The energy output is mostly in the form of radiation from the accretion disk, not in the form of collimated outflows. The mass of the black hole is tied to the mass of the galaxy. This is one of the most surprising discoveries in modern astrophysics. Supermassive black holes do not grow in isolation. They grow alongside their host galaxies, and there is a tight correlation between the mass of the black hole and the mass of the galactic bulge, the central concentration of stars surrounding the black hole. The relationship is not exact, but it is remarkably consistent across a wide range of galaxy types. A galaxy with a more massive bulge has a more massive black hole. A galaxy with a less massive bulge has a less massive black hole. The ratio is roughly 1 to 1,000. For every 1,000 solar masses in the bulge, there is about 1 solar mass in the black hole. That correlation suggests that the growth of the black hole and the growth of the galaxy are linked, that they are feeding off the same reservoir of gas and influencing each other through feedback mechanisms that we are only beginning to understand. The black hole at the center of M51 fits this pattern. The galactic bulge contains billions of solar masses worth of stars, and the black hole weighs about 1 million solar masses, right in line with the expected ratio. But how did it get that massive? How do supermassive black holes grow from stellar mass seeds to monsters weighing millions or billions of times the mass of the Sun? The process takes time. A black hole grows by accreting gas and by merging with other black holes. Each time the black hole pulls in a cloud of gas, it gains a little mass. Each time two galaxies collide and their central black holes merge, the resulting black hole is more massive than either of the original two. Over billions of years, through countless accretion events and mergers, the black hole grows. The early universe was a chaotic place, full of galaxy collisions and gas-rich environments that could feed black holes at high rates. The supermassive black holes we see today are the products of that early feeding frenzy, grown large through billions of years of accumulation. The collision between M51 and NGC 5195 may have played a role in feeding the black hole. Galaxy collisions funnel gas toward the center. The tidal forces from the interaction disrupt the disk, stirring up the gas and sending it inward toward the nucleus. Once the gas reaches the central regions, it can be captured by the black hole's gravitational field and added to the accretion disk. The collision does not directly throw gas into the black hole. The black hole is too small, the event horizon too tiny for a collision to hit it directly. But the collision can change the angular momentum of the gas, allowing it to spiral inward and eventually reach the black hole. The activity we see in M51 today, the X-ray emission and the ionization cones, may be a direct result of the interaction with the companion galaxy. The collision stirred up the gas, fed the black hole, and triggered the current phase of AGN activity. The black hole is not going to stay active forever. The accretion rate depends on the supply of gas. If the gas runs out, the black hole goes quiet. The disk fades, the X-ray emission drops, the ionization cones disappear. The black hole is still there, still massive, still exerting its gravitational influence on the surrounding stars, but it stops glowing. It becomes dormant. The Milky Way's black hole, Sagittarius A star, is mostly dormant today. It accretes small amounts of gas, flares up occasionally, but it is not actively feeding the way it probably did billions of years ago. M51's black hole may follow the same path. The current activity is driven by the collision with NGC 5195, but that collision is a temporary event. Once the two galaxies merge and the gas is consumed or dispersed, the black hole will have less fuel, the activity will decline, the Seifert phase will end. The galaxy will become a normal spiral, or more likely an elliptical, with a quiet supermassive black hole sitting at the center, invisible except for the motion of the stars around it. The event horizon itself is unreachable. It is not a physical surface. It is a boundary in space-time, a point of no return. Once you cross the event horizon, every path you can take leads inward toward the singularity at the center of the black hole. There is no way out. Light cannot escape. Information cannot escape. Anything that falls in is lost to the outside universe forever. General relativity predicts that the singularity at the center is a point of infinite density, a place where the equations break down and the known laws of physics no longer apply. That prediction is probably wrong. Most physicists believe that quantum mechanics will eventually provide a description of what happens at the singularity, some kind of quantum gravity theory that smooths out the infinities and replaces the singularity with something less pathological, but we do not have that theory yet. For now, the singularity is a mystery, hidden behind the event horizon where we can never see it. The size of the event horizon depends on the mass of the black hole. For a non-rotating black hole, the radius of the event horizon, called the Schwarzschild radius, is proportional to the mass. A black hole with one solar mass has a Schwarzschild radius of about 3 kilometers. A black hole with 1 million solar masses has a Schwarzschild radius of about 3 million kilometers. That is roughly twice the distance from the Earth to the Sun. That sounds large, but on galactic scales it is microscopic. The Milky Way is 100,000 light-years across. A 1 million solar mass black hole has an event horizon that is only about 2/100ths of an astronomical unit across. You could fit the entire event horizon inside the orbit of Mercury with room to spare. The black hole is a point, a speck, a tiny region of space that happens to contain more mass than 1 million suns, and yet that tiny region dominates the dynamics of the entire galactic core, pulling in gas, heating it to millions of degrees, and shaping the structure of the surrounding galaxy. The black hole is also spinning, almost certainly. Black holes can have angular momentum, and most black holes in the universe probably spin because the gas that falls into them has angular momentum. As the gas spirals into the black hole, it adds not just mass but also spin. A spinning black hole, called a Kerr black hole, is different from a non-rotating Schwarzschild black hole. The event horizon is smaller, The innermost stable orbit is closer, and there is an additional structure called the ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. The ergosphere is where the energy for relativistic jets is extracted. Magnetic fields threading the accretion disk can tap into the rotational energy of the black hole and channel it into the jets. The process, called the Blandford's-Najek mechanism, is one of the most efficient energy extraction methods in astrophysics. A rapidly spinning black hole can convert a significant fraction of its rotational energy into jet power. M51's black hole may be spinning, but the lack of strong jets suggests either that the spin is moderate or that the magnetic field configuration is not right for launching powerful jets. The future of the black hole depends on the future of the galaxy. When M51 and NGC 5195 finally merge, their central black holes will merge too. The process will take millions of years. The two black holes will spiral inward, losing orbital energy through gravitational wave emission. As they get closer, the gravitational waves get stronger and carry away more energy. Eventually, the two black holes will collide and merge in a fraction of a second, releasing a burst of gravitational waves so powerful that it will ripple across the universe. Instruments like LIGO and Virgo have detected gravitational waves from merging black holes, though so far only stellar mass black holes in the range of a few to a few dozen solar masses. The merger of two supermassive black holes would produce a much stronger signal, but at a much lower frequency. Future space-based gravitational wave detectors like LISA are being designed to detect those signals. When M51's black holes merge, the event will send gravitational waves propagating outward at the speed of light. Those waves will not reach Earth for another 23 million years, but when they do, they will carry information about the masses and spins of the merging black holes, encoded in the frequency and amplitude of the waves. The merger will also create a recoil. When two black holes merge, the gravitational waves are not emitted symmetrically. There is a preferred direction, and the asymmetry gives the merged black hole a kick, a recoil velocity that can be hundreds or even thousands of kilometers per second. If the kick is strong enough, it can eject the merged black hole from the galactic core entirely, sending it flying out into the halo or even into intergalactic space. That probably will not happen with M51. The recoil velocities depend on the mass ratio and spins of the merging black holes, and for most configurations the kick is not strong enough to eject the black hole, but it can displace it. The merged black hole might not sit exactly at the center of the new galaxy. It might be offset by a few light years, orbiting the true gravitational center until dynamical friction drags it back to the middle. Observations of some galaxies have found evidence for off-center black holes, possibly the result of recent mergers where the recoil has not yet dissipated. The black hole is not just a passive observer at the center of the galaxy, it is an active participant in the galaxy's evolution. The energy output from the accretion disk and the jets, if they exist, can heat the surrounding gas and prevent it from cooling and collapsing into new stars. This is called AGN feedback, and it is one of the main mechanisms by which supermassive black holes regulate star formation in their host galaxies. Without feedback, galaxies would convert all their gas into stars very quickly. With feedback, the process is slower, more controlled. The black hole heats the gas, drives it outward in winds or jets, and keeps it from collapsing. The result is a galaxy that forms stars at a steady rate over billions of years, rather than exhausting its gas supply in a single burst. M51 is in the middle of that process. The black hole is active, but not so active that it has shut down star formation entirely. The spiral arms are still glowing. The stellar nurseries are still collapsing. The balance between star formation and feedback is delicate, and the black hole is one of the key players in maintaining that balance. The supermassive black hole at the center of the Whirlpool is a reminder that galaxies are not just collections of stars. They are systems, interconnected webs of gas and stars and dark matter and black holes, all influencing each other through gravity and radiation and feedback. The black hole is not separate from the galaxy. It is part of the galaxy, as much a component of the system as the spiral arms or the stellar nurseries or the blue supergiants burning themselves to death. The black hole grew alongside the galaxy, fed by the same gas that formed the stars, shaped by the same collisions that triggered the spiral arms. It is the gravitational anchor, the point around which everything else orbits, the engine that powers the AGN activity, the regulator that controls the star formation. And it is still growing, still accreting, still shaping the galaxy even now. 23 million years ago, when the light we are seeing today left M51, the black hole was already there, already massive, already feeding. It has been there for billions of years, growing slowly, accreting gas one atom at a time, merging with smaller black holes during past collisions. And it will still be there billions of years from now, long after the blue supergiants have exploded, long after the spiral arms have faded, long after the collision with NGC 5195 has ended in a final merger. The black hole is patient. It does not care how long the process takes. It just pulls inexorably on everything around it, waiting for the gas to spiral inward, waiting for the next meal, waiting for the next merger. The whirlpool will change. The black hole will endure. And that endurance, that permanence in the face of cosmic chaos, is what makes supermassive black holes so central to our understanding of galaxies. They are not anomalies. They are not oddities tucked away in distant corners of the universe. They are universal features, present in almost every large galaxy we have ever observed. They are the anchors, the engines, the regulators. They are the hearts of galaxies, hidden behind veils of dust and gas, invisible to our eyes but undeniable in their effects. M51's black hole is just one example, one data point in a vast catalogue of supermassive black holes scattered across the cosmos. But it is a good example, close enough to study in detail, active enough to show us what these objects do when they feed, embedded in a galaxy that is beautiful enough, organized enough, and well studied enough to serve as a laboratory for understanding how galaxies and black holes evolve together. The whirlpool is not just showing us how stars are born and how spiral arms form and how galaxies collide. It is showing us how black holes shape the universe. And that lesson, that insight into the role of black holes in galactic evolution, is one of the most important things we have learned from studying M51. The galaxy is a mirror, and in that mirror we see not just the whirlpool, but ourselves, our own galaxy, our own place in the cosmic story. 23 million light-years is a long way to travel for a lesson, but that is exactly what the light from the Whirlpool Galaxy has done. It left M51 when our planet was unrecognizable, when the ancestors of every living thing on Earth were vastly different from what they are today, when the continents were drifting into configurations that would not persist. And it arrived here, at telescopes scattered across the surface of this small rocky world, carrying with it a message about how galaxies work, about how they are born, how they grow, how they collide, how they form stars, how they die. The whirlpool is not just a beautiful object in the night sky. It is a textbook, and we have been reading it for nearly 250 years. What have we learned? Start with the basics. M51 is a grand design spiral galaxy, one of the clearest examples of the type in the entire observable universe. It has two dominant spiral arms, perfectly symmetric, sweeping outward from a bright yellow core in a pattern that looks more like a blueprint than an accident of gravity. Those arms are not solid structures. They are density waves, regions where gas piles up as the galaxy rotates, compressing the hydrogen until it collapses and ignites into new stars. The arms glow blue with the light of massive young stars, and pink with ionized hydrogen gas heated by ultraviolet radiation. The star formation is concentrated in the arms because that is where the density waves do their work, squeezing clouds until gravity wins and protostars begin to form. The process is continuous, self-sustaining, and has been running for hundreds of millions of years. The galaxy is a factory. It takes hydrogen and turns it into stars, and it does so at a rate that can continue for billions of years, as long as the gas supply holds out. The spiral structure itself is the result of a collision. NGC 5195, the smaller companion galaxy sitting at the end of one of M51's arms, is not just passing by. It is locked in a gravitational dance with the Whirlpool, a slow-motion interaction that has been reshaping both galaxies for tens of millions of years. The tidal forces from the encounter triggered density waves in M51's disk, organizing the gas and stars into the two dominant arms we see today. Without that collision, the galaxy would probably still have spiral arms, but they would be weaker, less symmetric, more like the messy multi-arm spirals that are far more common in the universe. The collision gave M51 its structure. It turned a normal spiral into a grand design spiral, a showcase object that looks the way a galaxy is supposed to look. The beauty of the Whirlpool is a direct consequence of violence. The interaction is not over. The two galaxies are still pulling on each other, still exchanging material, still reshaping each other's structure. A faint bridge of gas and stars connects them, a visible scar from the last close pass. The bridge will fade over time, but the interaction will continue. NGC 5195 is on a decaying orbit. Each pass brings it a little closer to M51. Eventually, in a few 100 million years, the two will merge completely. The collision will trigger a burst of star formation as the gas in both galaxies is compressed and funneled toward the center. The spiral arms will be disrupted. The grand design structure will be destroyed. What emerges from the merger will probably be an elliptical galaxy, a featureless blob of old stars with no spiral arms and no ongoing star formation. The Whirlpool, as we know it, is temporary. It is a moment in the long history of a galaxy, a brief period when the conditions were just right for a perfect spiral to emerge. That moment will not last forever. At the center of the galaxy, buried beneath layers of stars and gas, there is a supermassive black hole. It weighs about 1 million times the mass of our Sun, maybe more, and it is actively feeding. Gas from the surrounding region is spiraling inward, forming an accretion disk that glows in X-rays as the material heats to millions of degrees. The black hole is not a quasar. It is not tearing the galaxy apart. But it is active enough to classify M51 as a Seyfert galaxy, a type of active galactic nucleus where the central black hole is accreting at a moderate rate. The energy output from the black hole is shaping the gas in the galactic core, heating it, ionizing it, driving it outward in winds that regulate star formation. The black hole is not just sitting at the center. It is an active participant in the galaxy's evolution, a regulator that controls how fast the galaxy can turn gas into stars. The interaction with NGC 5195 has funneled extra gas toward the center, feeding the black hole and triggering the current phase of activity. When the merger is complete, the two black holes will merge as well, releasing a burst of gravitational waves that will ripple across the universe. Those waves will not reach Earth for another 23 million years, but they will carry information about the masses and spins of the merging black holes, encoded in the frequency and amplitude of the signal. The spiral arms of M51 are packed with stellar nurseries, vast clouds of hydrogen collapsing under their own gravity and igniting into clusters of newborn stars. The largest of these nurseries span hundreds of light years and contain thousands of stars. The massive stars, the blue supergiants that dominate the light output of the arms, live fast and die young. They burn through their fuel in a few million years, then explode as supernovae, scattering heavy elements into the surrounding gas and triggering new rounds of star formation in the compressed shells at the edges of the remnants. The cycle is relentless. Birth, life, death, and in the debris of death, the seeds of new birth. The Whirlpool has been running this cycle for billions of years, building up the metallicity of its interstellar medium, enriching the gas with carbon and oxygen and iron, creating the conditions necessary for rocky planets and, in theory, life. The Chandra X Ray Observatory has mapped M51 in high-energy light, revealing over 400 X-ray sources scattered across the galaxy. Most of those sources are neutron stars and stellar mass black holes, the remnants of massive stars that exploded as supernovae. Some are accreting gas from companion stars, heating the infalling material to millions of degrees and glowing brightly in X-rays. Others are isolated, cooling remnants that will eventually fade into invisibility. The diffuse X-ray emission that fills the spaces between the bright point sources comes from hot gas heated by supernova shockwaves. The spiral arms are not just star formation factories, they are graveyards. Every bright blue cluster will someday explode, and when it does, it will leave behind a hot bubble of X-ray emitting gas that will persist for millions of years before cooling and dispersing. So that is M51, a grand design spiral shaped by a collision, forming stars at a high rate, enriching the interstellar medium with heavy elements, regulated by a supermassive black hole at its center. It is a dynamic system, a living, breathing galaxy in the middle of a violent transformation that will take hundreds of millions of years to complete. And it is close enough and bright enough and oriented just right that we can study it in detail, mapping its structure, measuring its star formation rate, tracking the motion of gas and stars, observing the effects of the black hole, watching the interaction with the companion galaxy play out in real time, or at least in the closest thing to real time that a distance of 23 million light-years allows. Now ask the harder question. Why does any of this matter? M51 is one galaxy among hundreds of billions. It is not the largest, not the closest, not the most active, not the most unusual. It is a nice example of a grand design spiral, a useful laboratory for studying galaxy collisions and star formation and active galactic nuclei. But it is not unique. There are other grand design spirals. There are other interacting galaxies. There are other Seyfert galaxies. What makes the Whirlpool special? The answer is geometry. M51 is face-on. When we look at it, we are looking down at the plane of the disk, seeing the spiral arms spread out in front of us like a map. Most spiral galaxies we observe are tilted at an angle, which makes it hard to see the arm structure clearly. Some are edge-on, which gives you a beautiful thin disk view but hides all the internal detail. The Whirlpool sits almost perfectly perpendicular to our line of sight. Every feature is visible. Every process is on display. The spiral arms, the stellar nurseries, the supernova remnants, the tidal bridge to the companion galaxy, the active nucleus at the center, all of it is laid out in a configuration that we can map and measure and study. M51 is legible in a way that most galaxies are not, and that legibility makes it invaluable. We live inside a spiral galaxy. The Milky Way is a barred spiral, slightly different from M51's grand design structure, but built on the same principles: gas, stars, dark matter, spiral arms, a supermassive black hole at the center. The problem is that we cannot see the Milky Way from the outside. We are embedded in the disk, looking out through layers of stars and dust and gas that obscure our view of the galactic structure. We can map the Milky Way, but it is hard. We have to piece together the structure from indirect measurements, tracking the motion of gas clouds and star clusters, measuring distances to objects scattered across the sky, building up a picture of the galaxy one data point at a time. The process is slow and uncertain, and there are large regions of the Milky Way that we still do not understand very well. M51 lets us cheat. It gives us a view of a spiral galaxy from the outside, a perspective we can never have on our own galaxy. We can see how the spiral arms are organized, where the star formation is concentrated, how the density waves move through the disk, how the gas flows from the inter-arm regions into the arms and back out again. We can watch the interaction with a companion galaxy and see how tidal forces reshape the structure. We can measure the effects of the central black hole and compare them to what we see in the Milky Way's center. Every observation we make of M51 teaches us something about how spiral galaxies in general work. And because the Milky Way is a spiral galaxy, that means every observation of M51 teaches us something about our own galaxy. The comparison is not perfect. The Milky Way is larger than M51, with a diameter of about 100,000 light-years compared to the Whirlpool's 77 to 89,000. The Milky Way has a central bar, a rectangular structure of stars extending from the core, which M51 does not have. The Milky Way's central black hole, Sagittarius A star, weighs about 4 million solar masses, roughly 4 times heavier than M51's black hole. And the Milky Way is not currently interacting with a large companion galaxy the way M51 is interacting with NGC 5195. We have dwarf galaxies orbiting us, and we are slowly shredding them into streams of stars, but we are not in the middle of a major merger, not yet. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, and that collision will reshape both galaxies in ways that are probably similar to what is happening to M51 right now. But that is billions of years in the future. For now, the Milky Way is relatively isolated, forming stars at a steady rate, regulated by its central black hole, slowly accumulating heavy elements in its interstellar medium. Despite the differences, the underlying physics is the same. Both galaxies are rotating disks of stars and gas held together by gravity and dominated by dark matter. Both have spiral arms driven by density waves. Both are forming stars in the arms and enriching the interstellar medium with the debris of supernovae. Both have supermassive black holes at their centers that grew alongside the galaxies and now regulate star formation through feedback. The details differ, but the broad story is the same. M51 is a proxy for the Milky Way. It is a laboratory where we can study processes that are happening in our own galaxy but are easier to observe in the Whirlpool because of the favorable viewing angle. Astronomers have used M51 to test theories of spiral structure, to measure the efficiency of star formation in density waves, to study the life cycle of massive stars, to map the distribution of supernova remnants, to understand how galaxy collisions trigger starbursts, to probe the structure of active galactic nuclei. Every one of those studies has implications for the Milky Way. When we figure out how the density waves in M51's spiral arms trigger star formation, we are also figuring out how the density waves in the Milky Way's arms work. When we measure the accretion rate onto M51's central black hole, we are learning about the processes that regulate accretion onto Sagittarius A star. When we watch the interaction between M51 and NGC 5195, we are seeing a preview of what will happen when the Milky Way collides with Andromeda. The whirlpool is a mirror, and in that mirror we see ourselves. M51 also serves as a benchmark for understanding galaxy evolution more broadly. Galaxies do not form in isolation. They grow by accreting gas from the intergalactic medium, by colliding with other galaxies, by merging with smaller companions. The history of any given galaxy is a story of accumulation, interaction, and transformation. The early universe was full of small, irregular galaxies, clumps of stars and gas that had not yet organized themselves into the grand structures we see today. Over billions of years, those clumps collided and merged, building up larger galaxies. The spiral galaxies we see in the universe today are the products of that long process. Most of them have experienced multiple collisions over their lifetimes. Most of them are still accumulating smaller galaxies. The Milky Way is currently eating several dwarf galaxies. Andromeda is doing the same. M51 is in the middle of devouring NGC 5195. This is normal. This is how galaxies grow. The whirlpool is showing us what that growth process looks like in action. The tidal bridge, the distorted spiral arms, the enhanced star formation, the funneling of gas toward the central black hole, all of it is a snapshot of a galaxy in the act of consuming another galaxy. The process is violent, but it is not destructive in the sense of obliterating the galaxies. It is transformative. The two galaxies are being reshaped, their structures altered, their star formation rates elevated, their black holes fed. When the merger is complete, the resulting galaxy will be larger and more massive than either of the original two. It will contain all the stars from both galaxies, plus the new stars that were born during the collision. The heavy elements ejected by supernovae during the merger will enrich the interstellar medium, making it easier for future generations of stars to form rocky planets. The merged black hole at the center will be more massive than either of the original black holes, sitting at the gravitational anchor of the new system. The merger is not an ending, it is a transformation, and M51 is letting us watch it happen. The role of active galactic nuclei in the cosmic web is another area where M51 has been instructive. The universe is not a smooth, featureless expanse. It is structured, organized into a vast network of filaments and voids called the cosmic web. Galaxies are not distributed randomly. They cluster along the filaments, drawn together by gravity into groups and clusters and superclusters. The largest structures in the universe are these superclusters, vast collections of galaxy clusters spanning hundreds of millions of light years. And at the centers of many of those clusters sit giant elliptical galaxies with supermassive black holes weighing billions of solar masses. Those black holes are often active, accreting gas and pumping out enormous amounts of energy in the form of radiation and jets. The energy output from those black holes heats the gas in the surrounding cluster, preventing it from cooling and collapsing into new stars. The feedback is so strong that it can regulate star formation across an entire galaxy cluster, affecting hundreds or thousands of galaxies. M51 is not in a massive cluster. It is part of a smaller group, the M51 group, which contains only a handful of galaxies. But the physics is the same. The black hole at the center of M51 is accreting gas, heating the surrounding medium, driving outflows. The energy output is lower than in the giant ellipticals at the centers of clusters, but the process is identical. By studying M51, we can understand how AGN feedback works in a less extreme environment. We can see how the black hole regulates star formation in a normal spiral galaxy rather than in a massive elliptical, and we can extrapolate those results to the larger population of active galaxies scattered across the universe. M51 is a laboratory for studying feedback, and the lessons we learn from it apply to galaxies at all scales. The galaxy is also teaching us about the life cycle of galaxies. Spiral galaxies like M51 do not last forever. Over time, as they collide and merge with other galaxies, they lose their spiral structure and transform into elliptical galaxies. Ellipticals are featureless blobs, dominated by old red stars with little or no ongoing star formation. They are the end state of galaxy evolution, the final product of billions of years of mergers. The transformation from spiral to elliptical is not instant. It takes hundreds of millions of years, maybe longer. But the process is inevitable. Every major merger pushes a spiral galaxy closer to the elliptical phase. M51 is in the middle of that transformation. It is still a spiral, but the merger with NGC 5195 is the first step toward becoming an elliptical. When the two galaxies finally merge, the spiral arms will be disrupted. The disk will be puffed up by the chaotic motions of the stars. The star formation will spike during the collision, then decline as the gas is exhausted. What remains will be an elliptical galaxy, a relic of the beautiful spiral that once was. The Milky Way will follow the same path. When we collide with Andromeda, the two galaxies will merge into a single elliptical. The spiral arms will be destroyed. The disk will be disrupted. The Sun, if it is still around, will be flung into a new orbit in the merged galaxy, possibly ending up in the halo rather than the disk. The night sky will look completely different. The stars will be distributed more evenly, without the concentrated band of the Milky Way running across the horizon. The star formation will decline. The galaxy will age. This is the future of every spiral galaxy in the universe. M51 is showing us what that future looks like. There are still questions, lots of them. Despite decades of observations, M51 has not given up all its secrets. The exact mass of the central black hole is uncertain. The mass of NGC 5195 is uncertain. The timeline of the interaction, how many times the two galaxies have passed each other, is uncertain. The star formation rate is well measured, but the efficiency of star formation, the fraction of gas that actually turns into stars rather than being blown away by feedback, is still debated. The distribution of dark matter in the halo is inferred from the rotation curve, but the details are murky. The structure of the accretion disk around the black hole, the presence or absence of jets, the geometry of the dusty torus, all of it is based on indirect measurements and models that have free parameters. Every observation we make answers some questions and raises new ones. That is how science works. M51 is not a solved problem. It is an ongoing investigation. Future observations will help. The James Webb Space Telescope is already observing M51 in the infrared, mapping the dust distribution and probing the stellar nurseries hidden inside the densest clouds. Webb's sensitivity will allow it to see individual star clusters forming in the spiral arms and measure their ages and masses with unprecedented precision. The next generation of ground-based telescopes, the Extremely Large Telescope, and the 30-meter telescope and the Giant Magellan Telescope, will be able to study M51 in even greater detail, resolving structures on scales of a few light-years and tracking the motion of gas and stars in the disk. The Square Kilometre Array, a radio telescope currently under construction, will map the distribution of neutral hydrogen across the galaxy, revealing the raw material for star formation and tracing how the gas flows through the spiral arms. And future space-based gravitational wave detectors like LISA will be able to detect the merger of M51's black holes when it happens, hundreds of millions of years from now, long after humanity is gone, but recorded in the ripples of space-time that will wash over whatever comes after us. M51 has already taught us an enormous amount. It has shown us how spiral arms form, how galaxy collisions trigger star formation, how supermassive black holes grow and regulate their host galaxies, how massive stars live and die and enrich the universe with heavy elements. It has given us a view of a spiral galaxy from the outside, a perspective we can never have on the Milky Way. It has served as a laboratory for testing theories of galaxy evolution and a benchmark for understanding the life cycle of galaxies, and it has done all of this while being one of the most beautiful objects in the night sky, a grand design spiral that looks the way a galaxy is supposed to look. But the deeper lesson of M51 is not about the galaxy itself. It is about what the galaxy represents. The Whirlpool is a single point of light in a universe that contains hundreds of billions of galaxies. Most of those galaxies are too far away or too faint or too badly oriented for us to study in detail. M51 is an exception. It is close enough and bright enough and positioned just right that we can see its structure clearly. And because we can see it clearly, we can learn from it. We can use it as a proxy for all the other galaxies we cannot see as well. We can extrapolate from M51 to the Milky Way, to Andromeda, to the galaxies in the Virgo cluster, to the galaxies at the edge of the observable universe. The Whirlpool is not unique, it is typical, and that is exactly what makes it so valuable. The collision between M51 and NGC 5195 is not an isolated event. Galaxy collisions are happening all the time, all over the universe. The early universe was full of collisions, small irregular galaxies smashing together and merging into larger structures. The present-day universe is still full of collisions, though they are less frequent now because the expansion of space has spread the galaxies farther apart. But in regions where galaxies are clustered together, collisions are common. The Milky Way is slowly shredding several dwarf galaxies. Andromeda is doing the same. In a few billion years, the Milky Way and Andromeda will collide. The process playing out in M51 is playing out everywhere. The Whirlpool is not an anomaly. It is a snapshot of a process that has been shaping galaxies for the entire history of the universe. And that process, that long, slow transformation of small galaxies into large galaxies through collisions and mergers, is how structure formed in the universe. The Big Bang gave us a smooth, expanding cloud of hydrogen and helium. Gravity turned that cloud into stars and galaxies. Collisions turned those galaxies into larger galaxies. Feedback from stars and black holes regulated the process, preventing the gas from collapsing too quickly and allowing star formation to continue over billions of years. The result is the universe we see today, a vast web of galaxies clustered along filaments, each galaxy a collection of billions of stars, each star a nuclear furnace turning hydrogen into heavier elements, each generation of stars enriching the interstellar medium and setting the stage for the next generation. M51 is one node in that web, one galaxy among hundreds of billions. But it is a node we can see clearly, and by studying it we can understand the web. There is something humbling about the fact that the light reaching our telescopes left M51 23 million years ago. The galaxy we are seeing no longer exists in that configuration. The stars we see as bright blue clusters have long since exploded. The gas we see in the spiral arms has collapsed into new stars or been blown away by supernovae. The black hole at the center has accreted more mass. The companion galaxy has moved farther along its orbit, or closer, or perhaps has already begun the final plunge toward merger. We are not seeing the galaxy as it is. We are seeing the galaxy as it was, frozen in time, a message sent across the void by photons that have been traveling for longer than our species has existed. By the time those photons reach us, the universe has moved on. The galaxy has changed. And yet the photons carry information, a record of the past, a snapshot of the whirlpool in a specific moment of its evolution. And we can read that snapshot. We can decode the message. We can learn from it. That is what astronomy is. It is not the study of the present. It is the study of the past. Every object we observe in the night sky is showing us what it looked like when the light left it, not what it looks like now. The sun we see is 8 minutes old. The stars we see are years or decades or centuries old. The galaxies we see are millions or billions of years old. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, is 13.8 billion years old. We are looking backward through time every time we point a telescope at the sky, and the farther we look, the farther back we see. M51 is 23 million years in the past. The most distant galaxies ever observed are over 13 billion years in the past, seen as they existed when the universe was only a few 100 million years old. Astronomy is a form of archaeology. We dig through time instead of dirt, and what we uncover is the history of the universe. M51 is part of that history. It is a chapter in the story of how galaxies form and grow and collide and transform. It is a lesson in the physics of star formation, the dynamics of spiral structure, the role of supermassive black holes, the effects of tidal interactions. It is a mirror in which we see the Milky Way, our own galaxy, our own place in the cosmic web. And it is a reminder that the universe is not static. Galaxies are not unchanging landmarks scattered across an empty void. They are dynamic systems, constantly evolving, colliding, merging, transforming. The grand design spiral we see today is a temporary configuration, a moment in the long history of a galaxy that has existed for billions of years and will continue to exist for billions more, though in a form we might not recognize. The whirlpool is not just a galaxy, it is a laboratory. It is a classroom. It is a window into processes that are happening all over the universe, processes that shaped the Milky Way, processes that will determine the future of every galaxy in existence. And it is close enough and clear enough and positioned